Hello. In this lecture, we're going to revisit decision trees, but this time we're going to see an application of decision trees that allows them to learn behavior through observation. This could be as a pre-training phase or possibly even interactively learn. So the decision making will be driven by these observations. So let's start off by considering this game that probably many of you have played in grade school, 20 questions. So the game of 20 questions is one kid will imagine something in their head without telling anyone. And it can often be a theme like an animal. So you imagine an animal in your head, you don't tell anyone. And you then the other kid or possibly multiple kids will ask questions of the person who imagined the animal. And these questions have to be true or false, or yes or no. And the goal is to figure out what the animal is within 20 questions. And then, so the kid that's asking the questions wins. Otherwise, if it takes more than 20 questions, the person who imagined the animal wins. And so the idea in the game is to ask questions that work down to a smaller and smaller subset of all animals as quickly as possible. And so this is also often like a programming assignment in introductory programming classes. You can find several examples of it online. So you might imagine, well, how can we go about building a decision tree for the 20 questions scenario? And so we'll start off with a simple approach for how to do this. So first thing we need is that we need a list of our objects, in this case, a list of animals. And then we also need to have a set of attributes that some of these attributes will be common across multiple animals. But the idea is that you have enough attributes that each animal has a distinct configuration of attributes. So we can put these attributes in a pool, and we want to select from this pool or set of attributes. We want to select from them in such a way that we're picking the attribute that best discriminates between the current set. So whatever the current set we're working with is, we want to basically come as close as we can to evenly splitting the group in half. So really we're sort of motivated about making like a balanced binary tree. Anytime that you split the set of attributes in half, then you will repeat this recursively, and you'll keep working your way down through the tree, so always selecting attributes to split. And then, of course, that attribute no longer is relevant in subtrees as we work down. So you pick an attribute to split on, you make a left branch for yes or no, and then a right branch for the opposite. And then you keep working your way down until you get to the point where ideally you'll have a single leaf node that is the animal in question. Now, there's a few practical concerns that you run into, like occasionally you'll have attributes that are maybes or unknowns for your animals, or in those cases you can't, your attribute doesn't discriminate, so you would pass those maybes down both branches, and then hopefully a later attribute will do a better job with those sort of wild card type scenarios. And you might also get to the point where you run out of attributes. And so if that happens, you can always fall back to asking just very straightforward questions. So if you got down to, say, like a set of different birds, you could say, is it a chicken? Yes or no. And then if you get it right, of course you're done. But if not, then you would ask, like, is it an owl? Is it some other sort of bird? And you just keep working your way through. But ideally, you would, if you ended up with a tree like that, you would add more attributes. It's also possible that you can end up where you know the animal, but you haven't exhausted all your attributes. So of course, you're not going to continue to recursively generate the tree with unnecessary decisions. So you would drop out early. But this is a really straightforward thing to implement. It's not particularly difficult. The way that this, at least as presented right now, is pretty simple. And that's because we only have one example of each of the animals. So there's only one line in the table for chicken and one for owl and so on. So that makes things easy. And also we only have these yes or no questions that we're dealing with. So that really simplifies the problem. But as we see, if we get a little bit more complicated scenarios, this whole issue of figuring out what decision best discriminates your set of objects, or they could instead of being objects, they could be like actions that that an agent is trying to decide upon. And so we'll see how to deal with, like, as this problem, we generalize this problem, we'll see how to work with it. So the real power of decision trees comes from their ability to learn. So the decision trees we've seen before, the concept is very simple, and it can be pretty tedious to try to design and maintain a decision tree. But the automation that's possible with learning can make them a lot more powerful. And so there are a number of different algorithms and variations of algorithms that can be used, but probably the most well-known is from Quinlan's work. So this is the iterative dichotomizer 3 algorithm, but typically you just see it ID3. And this particular algorithm is a way that it has a general solution for how to train our decision tree based on observations. So we can typically we would use this to predict human decision making. So we would train on human behavior, and but we could also use it for in addition to like decision making in say like a strategy game. We could also use it for like classification problems, like what is something. But we'll have some object or a situation that's described by a set of attributes, very much like what we saw with the 20 questions. Now, these attributes, they can be discrete, like we showed with the 20 questions, but they can also be continuous values. So in the case of continuous values, we have to find a way to split the range of possible continuous values. And the idea is that we're trying to predict what the outcome is that the human made. So that could either be like a decision for like a gameplay behavior, or it could be a classification, like looking at images and deciding what object is seen, or maybe what the enemy is currently doing. You might have like in a video game, that sort of thing. All right, so we have this current set of decisions with attributes that describe these decisions, and we're trying to decide how best to split these up similarly to the 20 questions. So we want to choose the best one, whatever does the best job of splitting them up. And now, before I said how that did the best job of discriminating between two sets, but more formally, this is with decision trees, with learning, this is the analysis done is based on information theory. So the best attribute to use for our decision to split is going to be whichever attribute will gain the most information once we make that split. So good attributes are going to make homogeneous sets, and that's not always going to be the case with messy real world data, but that's the goal. And the idea is just recursively go down. Every time a new decision is added based on picking the best one, we're going to go recursively down each edge and further split the groups that have already been divided and split. So here is a classic example for learning D-trees. This is some data about potential customers at they're going out to eat, and they encounter different scenarios at the restaurant they visit, and we're trying to figure out, predict or classify the customer based on how likely they are to wait to be served. So these are restaurants that all have potentially some amount of wait. So it might be like 0 to 10 minute wait, or 30 minutes to an hour, 10 minutes to a half hour, that sort of thing. And so there's several different attributes that we have about each of these scenarios. So again, we're trying to classify based on whether the target or the candidate customers actually wait. And some of the attributes are, so alt is there an alternate available? Bar is if the restaurant has a bar included. Fry is short for Friday, meaning is it a Friday or a Saturday? Pat is the amount of patrons that are already at the restaurant. Hun is whether the candidate customers are hungry. Rain is exactly that, if it's raining or not. Res is short for reservation. And then there is the type for what type of food it is, and est is the short for estimate of how long the wait is. So here we have just some example data, and you can see that of all of these different attributes, you can follow along left to right to see what they are for any particular example. And then you have your target weight, which again, that is whether the candidate customer chose to wait or not. So you'll see a mixture of true and false values. So this is the sort of data we want to be able to pick attributes, and whichever attribute does the best job of splitting up the data, that will be like the root decision of the decision tree. And then we will advance from there on to either eventually to both, along both branches, to the left and to the right, recursively deciding how further to continue splitting up the data. The idea is that if we have any future scenarios, we will have, we'll be able to determine the attributes of the new scenario. and then be able to guess. And so you can imagine this would be maybe useful for like if you owned a restaurant, for deciding how to maximize your profits and or keep the most customers to stay rather than to leave. All right, so a good attribute is going to be one that does a good job of splitting in a way where all are positive or all are negative. We could pick anything to split and not end up with a good result. So for instance, the type of food with this particular data set, if we chose the attribute for type, you can see, well, clearly it does split up the data, but it doesn't split it up in any sort of usable way. So you end up with the French food, you have one positive and one negative. Same with Italian. The Thai food, we have more people, but it's still split with 2 positive examples and 2 negative, and burger as well. So there was no progress that was made by using type. But if we split by the number of patrons already present in the restaurant, you see that this particular data set, so there's 3 categories for the patron. So we have none. Now, if there's nobody there, then the customer's not willing to wait. But if there are some patrons there, then they are very likely to wait, because all the examples are positive of waiting. But then if the restaurant is full, you can see that, well, it didn't work perfectly here. So there's a little bit of it's not like a binary thing. When we pick the best split, that it's kind of a continuum potentially. If you have a lot of attributes, some attributes might only be slightly better at splitting the data than another attribute. All right. So let's say that we've gone through this process. We've sort of just been kind of high level talking about how we go about selecting the attribute. But let's say that we have done this and we've built our decision tree. So we'd end up with something like this, where in this case, clearly it's not a binary tree. So that's one thing we notice right away, because some of our attributes have enumerations of like different categories. There is hunger, which is a binary, so we get the 2 branches there. But patrons, we have none, some, and full. And for the type of food, that's a 4-way split. And then Friday, Saturday, again, is binary. So we have a variable number of branches according to what these attribute decisions are. But you can see that we could parse through the tree with some new example, and then that would allow us to end up with a decision. So whether or not it's the right decision will depend on what the application is. If we just need some sort of like reasonable behavior for, say, a video game agent, then there's not necessarily a right or a wrong answer. But if you're trying to classify something, then that maybe depending on what the repercussions of that decision are, then maybe that is very important. So here's a new example. That this is a video game scenario. So this will be somewhat similar to what we just saw with the restaurant, except just this game-focused scenario. So this is, should the agent attack? And the idea here is that we have data from a human player. So we're trying to make an agent that does a good job of playing like an RPG type game that's got random encounters with enemies. So different enemies are popping up all the time. And the the player or the agent in this case doesn't have to fight every single enemy that they encounter. They can skip some. So we have these attributes like, well, can the battle actually be bypassed? Whether or not there is loot available. If this particular battle is associated with unlocking an achievement, if you get the win, if the agent is on a quest, how much experience is available to get, the environment, so this is related to how favorable the terrain is, whether or not the enemy encounter is a mini boss, and a mini boss that needs to be beat in order to make further progress. Then we can consider the element of the enemy or the magic that the enemy uses, so like earth, air, fire, water. Estimated time for how long the combat will take, and so this can be categorized as quick, short, long, very long. And then team size, so that would be how many monsters are in the team. And that's also a category, so none, small, and large. So from those attributes, if we have a lot of example data that we're using to train from a human player, we might build a decision tree. So again, this relies on us being able to select attributes that do the best job of splitting up the data into these homogeneous groups, so that ideally, the end result classification is all one or the other. And so in this case, the classification is just two values of whether or not the agent should follow through with the encounter and try to defeat the monsters. Here's some example data based on the attributes that I just described. And so you can see the final column has the yes or no for deciding whether to attack. And so we've got all of these different examples. So we'll consider some possibilities here. So let's say that we look at the attribute for the elemental magic that's involved. And so in this case, we've got the indices of all the positive and negative records. This is a very small amount of data just for the example, but you can see that 1, 3, 4, 6, 8, and 12 are all the positive examples, and then we have similar number of negative examples shown. And so let's just say we pick the elemental magic involved as our split. And you can see this isn't a very good attribute to select, because while certainly we do split the data up into these 4 different branches, each one of them are perfectly balanced in terms of positive and negative examples. But with team size, and so this being 3 different categories, so a single enemy, a few, or many, you can see that that selection, we have much better results in terms of, like, for instance, the single team size of single. Then we have no positive examples and only negative examples. So you might imagine that a single enemy has not much in the way of any kind of reward or otherwise there's no benefit. It's just a waste of time, basically. But if there's a few enemies, then that probably balances out difficulty and danger, but still some potential for reward. Just my guess for this made up data. So we've got the 4 positive examples, no negative. Now, if there's many enemies, that is a situation where the downsides might begin to outweigh any potential benefit. So there's actually twice as many negative examples as positive examples. Now, this particular bit of the decision tree shown further splits by whether or not the agent is on a quest. And so if they're on a quest or not, that can further split the data. So of course, the example records or the rows in the data that are considered for the on quest split, well, this is a subtree. We've already whittled out the team size single and team size few. So the only data records we're considering are those that were passed down to the subtree for the team size mini. So you'll notice that the on quest true took all of the positive records, which were just the index 4 and 12. So it ended up where there's no positive records for on quest false side, but it did end up with a couple negative ones there. So yeah, keep that in mind. You're always reducing your set of data at each subtree as you go down through the decision tree. All right, so here is an example for starting with team size, which was the best option to select. Then on quest and element, and then finally for one of the branches we have we need to select an additional attribute for a decision, and that would be achievement. So this doesn't look like that first example decision tree that I showed you for this scenario, assuming that the first example was like the ideal tree and this one's looking different, well, most likely scenario that would lead to this is that we just didn't have enough example data to train on. So therefore, the selection of the best attribute, there wasn't enough data to properly identify what the best splitting attribute was. So yeah, it's just the algorithm can only do as well as the data that it is provided with. And this is a situation where we're supervising the learning process. So we need to provide it with the training data, and then we need to validate what the result of that training is through a test set. So back to this attribute selection issue, we've kind of been waving our hands and just saying it's the best one. And so we'll look a little more closely at how information theory can be applied for formalizing this selection here. So what we're trying to figure out is, well, how much information does something contain, like our set of attributes or a set of examples and the associated attributes. And then we're going to ask a question, and that the answer to the question is the information. And the amount of information depends on how much we already knew. So if whatever the amount of information that's gained is going to always be relative to what we already know. So an example might be like flipping a coin. And so you could like look at observations of flipping a coin to learn something about it. So we're going to use entropy as part of the information theory and the way in which we're going to assess how good an attribute selection works. So we're going to be measuring information in a set of these different examples or observations, and we're going to find out the amount of agreement between the examples. So if all of the examples are in the same action, then it would be zero entropy there. But if they're all evenly distributed and different, then we have high entropy, and so that would be 1, a value of 1. So that's the maximum entropy, actually. So if there are n possible answers, P1 through Pn, and Pi has a probability defined by this probability function of P sub I. If that is the selected answer, then the amount of entropy is this function h, where the equation is the sum over all the different possibilities, p sub I times log base 2 of p sub I, and the whole sum is negated. So let's look at if we just pick I, just one single I value. So we only have one possible value. And so that gives us this function here. So from 0 to 1, we have this kind of a skewed curve that looks really weird, but I think it's worthwhile to look at. So this doesn't really make any sense, because this scenario, it is basically saying that there's only this single possibility. But like if we're considering something like a coin flip, let's say, then we have the probability that you flip heads or flip tails. So this equation is really, it's degenerate at this point. But let's add in, well, I'll go back again so you can see it's the sum. So of all the possible answers, in the case of a coin, we have P sub 1 for like heads and P sub 2 for tails. That means that we're going to have the summation so we're going to have 2 of these P times log base 2 of P values. So we're going to have the sum of that. So I'll now go to that example. So we've got, this is just the summation that's expanded for 2. And the probability values, well, if you've got through some number of trials, if you have heads, then or some percentage of trials you have heads, then the other percentage you have tails. So I've basically set that up in this equation when I graphed the function here. So this is just graphing all possible values of like P sub 1 from 0 to 1. So that being the probability. So let's say this is, we're flipping a coin, and it has a variable likelihood of being heads and tails. It's not a 50-50 split necessarily. So it could be 0% of the time it's heads and always tails, or as we go sweep across the x-axis, we're transitioning from always tails to a 50-50 split in the middle, and then at the other end it is always heads. And so the x value that's passed into the x times log base 2x value, you'll see that the first term is just x, but the second term in the summation from the entropy equation, I put 1 minus x. So basically just saying whatever percentage is lost by heads, it's gained by tails. It's always going to be a total probability of 1. So the probability of heads plus the probability of tails always sums to 1. So that's why there's the x and the 1 minus x. But back to the graph, you can see that if heads and tails are equally likely, in this situation. So that is the the values are very tiny here, but like right in the middle of the x-axis, that's 0.5. And if you go up to the where the curve is, you see that it peaks right at 1. So that means we have maximum entropy, like in the coin toss scenario, we have maximum entropy if it's a fair coin that is equally likely to be heads or tails. Now this equation for entropy is flexible. We can apply it to other scenarios like the attributes that we saw in the examples used in our decision tree training. So that's what we're going to use as part of this determining how best to split our data. What attribute will we use for our decision? So for our training set, we have, at least in the example that we currently have, it's kind of like heads and tails in that there's two possibilities. There is that the agent should attack or just retreat and pass on the battle. So that's what we're looking for. So for our entropy, we have, for any given attribute, we can determine how much entropy is present based on how many positive examples we have and how many negative examples we have. And so you can see here, it's just like when we graphed the coin toss scenario. So we've only got the summation of the two terms. So where P is the number of positive examples and N is the negative examples. So we just have these ratios. And so the ratio is either, so we know the total number of examples is P plus N. So that's the denominator. And then you either have as the numerator either P or N, depending on which we're talking about, either positive or negative examples. So we can plug P over P plus N for positive examples, plug that in for the first of the entropy term, so that summation. And then we can plug in N over P plus N for the negative example for entropy. So when we are looking at an attribute, when it does the split, we can see very quickly for this example, we can just figure out, all right, well, what are the positive and the negative examples? So for like the attack behavior, we have an equal number of positive and negative. So overall for this scenario, we have full entropy. So the of all of the what was it, 12 records we have 6 of each. So we're starting off the whole scenario of when we're building our tree, we have an entropy of 1. So we're going to use the entropy as part of this remainder equation. And so the remainder equation, it is figuring out if, so we have some starting entropy. We just saw that what our starting entropy was. And what we're trying to do is figure out how much entropy remains after applying an attribute. So the input to the remainder function is whatever the attribute is, and then based on that, we're going to go through all of the different different answers that are possible for that attribute. So that would be like the different sort of categories. Some of them were binary, but some had like 3 or 4 levels. We're going to go through all of those. And then we're going to look at, for the instances of the particular attribute, we're going to have some positive and some negative examples. Or if we're lucky, we're just going to have all positive or all negative, which will be better. And so for that, we're going to take the sum across all of those different possible answers for the attribute. We're going to look at the ratio of the positive plus negatives for each of those answers. So we're taking the summation of this divided by the total answers, and then multiplying that by the entropy. So again, this is for each of the instances of that particular attribute. For that answer. And so you've got again, it's just like in this case we've got just the either the true or the false, or the fighting or not fighting. So we only need 2 values here. So we can see how this can work out with the poor attribute for the elemental magic. And so in this, as you recall, was the bad example where it didn't do anything at all to isolate our records into positive and negative examples. It split the data up 4 ways, but they were all still equally balanced, positive and negative. And so here you can see that we've got the 2 out of 12. We started again with a total of 12 records, and then so for water we have 2. So this is like a weighting factor. We're weighting the data. So 2 over 12, and then times the entropy of the positive and negative examples. So here, again, these values are indices. So this is index 1 and index 5. So that's why there's 1 over 2 and 1 over 2. So the entropy there. And then we have for fire 2 over 12 again, because there's only 2 examples, but the entropy is the same value again. And so all of this adds up. As if we continue on for air and earth, we end up with a remainder of 1 bit. And now this, we started with 1. So you can see here the remainder after doing the split is still exactly the same. But with team size, you can see how we've got much better, just looking at it, we can tell it's much better data because we're not balanced with the number of positive and negative examples. And so, so in this case, it ends up with a 0.459 bit. So we can see that there's a much better reduction with this remainder. So the information gained ends up being the entropy overall at the whatever step we are in the process. So what was the entropy that we started with minus the remainder if we select a particular attribute? We're going to do this for all of the available attributes wherever we are in the tree. So we might just assume we're at the very beginning, and so we have all attributes available. So we go through all of them, and we will compute this gain. And then for each, we're going to figure out, well, how much is it reduced? And again, this is all relative to what the initial entropy was. So if we already had poor entropy, it's going to account for that in the calculation, or later like as part of one of the subtrees, a subtree of the decision tree, then we're still going to have to make these decisions, but it's all going to be relative to what we're working with. So yeah, we at this point we can easily select which is the best to work with. All right, and so once you've made the selection, then you do the exact same thing recursively. So you will then be working with a new starting point for your initial entropy. So you won't have whatever the initial entropy at the root level, you won't have further in the tree. So for instance, after we've already done the split for team size, and we are on the branch for team size of many, we'll have 2 positive examples and 4 negative. So that's reduced entropy, and that's reflected by the left term. Let's see if I can get my mouse cursor to show up. So this example here, so you can see there's 2 for the positive. So 4, index 4 and 12 fill into this value 2. And for the negative examples, we have 2, 5, 9, and 10 indexes. And so that is the 4. But that is out of the overall 12 that we initially started with. So for the mini branch, it's only got the 6 total records, but we still are using the denominator of 12. So it's a reduced entropy because of the work that was accomplished by selecting team size. And then we're subtracting out the remainder that is based on the entropy for selecting OnQuest. Now there's only two levels for OnQuest, so the remainder is only going to have these 2 terms rather than the what I think we had 3 before with team size. And yeah, so we plug that in. Of course, we have these new entropy calculations in here as well. Those are based on what the distribution of positive and negative examples are for the left and the right branch. So left being false and right being true, and that's whether we're on quest or not. So that'll give us a new gain from that selection. And so if we have multiple attributes to select, we would again make the comparison. It's going to be fewer attributes, and it's going to be a lower starting entropy that we're going to be working with. Now, one sort of practical issue you can run into when you have data, especially like real world data, maybe you collected from a human player, is that you might end up with exactly the same attributes describing an outcome or maybe a decision of what action to take. You might have examples, 1 or more or 2 or more examples that go one way, say fight or not fight. So you have, say, the party size, the elemental magic, and all those attributes. They all perfectly match, but then you have examples in your table of data where the player chose to fight and the player chose not to fight. And so this is a bit of a tricky situation to deal with in terms of how to interpret and use the data. So you could either just go with the majority classification. So you could actually go through the data and determine what do you have the most of, and then maybe just only train on that. Or you could report the probability. So in addition to whether it was true or false, you might have what percentage, so that could be useful in real time, like a confidence score. So if if something's very high probability in the face of this noisiness, then you could be more likely to act upon it in terms of anything that's interpreting the results passed back from the decision tree. You might have some other components to your agent that's interpreting these recommendations from the decision tree, like maybe high-level strategy. So you still have other agent control that's filtering or interpreting what the decision tree is passing it. So it might be more likely to act if the data is more consistent. All right, so in terms of the algorithm, this is just a bit of pseudocode from Millington. So this is just a high level describing the process, and it involves just you continue to process the example data until it is empty, and if it is, then you just return a default value that has been already passed in. Otherwise, if all examples have the same classification, then of course you're just going to return that as the classification. Otherwise, if you might have run out of attributes, and so if that's empty, then you're going to use this majority value from the examples. So that's like what we're just talking about. And then otherwise, that means that we have the opportunity to pick an attribute and split and add some more decisions to the tree. And so this is where all the actual work is done. So this choose method is where we're determining the gain in information based on the entropy calculation, and then whatever attribute reduces the entropy the most, like what we just walked through. And so we make a new decision tree that's really going to be a subtree, and then we will iterate through and then recurse down once we make these splits. Now you can also use the decision tree in scenarios where there is continuous data. So all the data we saw was discrete, like enumerated categories or just true or false values. But if we have continuous data, what we can do is we're still going to have a fixed number of examples. So we can actually take all that data, sort according to whatever the attribute in question is. So it might be like a floating point value. We can just sort all of them in like lowest to highest. And then we can just start trying to all possible splits of the value. And then whatever gains the most information is the best split. So we might pick, say, the value like right in the middle, that whatever that index is. And so everything below the index will be 1/2, and then that index and everything above will be the other half. And then you can run through the whole calculation of information gain, just like we've been doing. So it's a little bit tedious to have to go through and do all this testing, but it's still possible when you do have continuous values. And so if we go back to our 20 questions example, we can see probably, well, I mean, it would be straightforward to use the ID3 algorithm that we've just looked at. And we could even modify the scenario a little bit so that it could handle some messy data. And a likely way in which you would have messy data is, well, you could like get help from like an online community to build this data for you. You could just say have a website where you ask people to list attributes and fill out the basically entries in the table that describe these different animals. In fact, I think I've seen a website that basically did this in like the early 2000s. So you could visit and play. You could play the 20 questions game online, and I believe that the way it worked is it threw in a few questions that would help further train it, so it would gain knowledge, and so it would get these new records basically. But it would be noisy because it's just random strangers off of the internet, and so it'd have to have ways of dealing with the noise, like that we discussed before. But it could be updated and become better and better at every time that the training was rerun. And so, like if you played against the website, it was the website would try to guess the animal or whatever the category was, the object that you were imagining in your head, and it would do a really good job of guessing. And there's also other implementations that aren't necessarily decision trees as well, but yeah, clearly we could use the ID3 algorithm to build our own 20 questions game. So just briefly, we can consider all the different possible configurations of a tree. So if you have, say, n attributes, then we're going to end up with just an incredible number of possible trees because of all of the different ways that we can order our decisions. So even with just 6 attributes, it's just like an impossibly large number. So there's a lot of power in terms of what a decision tree can represent, because there's so many different configurations. That means it's very flexible in terms of capturing these decision-making hierarchies. So we just briefly covered this a few slides ago. How do we assess our decision tree? And so that involves having a training set of data and then a test set. So in order to have a useful training data, we need a large enough amount of data that any problems with examples, especially related to noise that appears, we want to make sure we have good coverage of all of the scenarios that are likely to occur with whatever the scenario is, like playing a game. And we also want to have enough that it overpowers noise, or hopefully that'll be the case, that we'll have enough data that it kind of smooths things out. Now, we're going to have a lot of data, but we can't train on all of that data, because if we train on all of it, then we'll have no way to gauge how well it works. And so rather than like using it all up and then having to go and collect a bunch of new data, we can just split up our data into a training set and a test set. So that will ensure that when we're testing with data that was not used in training, so there won't be that that bias there of already having seen the examples before. So this training set allows us to produce this hypothesis, which is basically the expectation of how the test set should classify. So we can score our decision tree on how well it does in terms of picking like the right decision, for instance. And so we can actually we can go through dividing the data in different ways and retraining from scratch, for instance. And this can help us to figure out, well, how much data is necessary for training, and also, what's like the ideal amount. So we can like graph the data, for instance. So if we vary the training set size relative to the test set, and are also shuffling things around, selecting different amounts, and again, always recreating our decision tree, we can look to see how well our hypothesis is working compared to the test set. So we're going to have like a scoring metric. So if we're training on a very small number, well, we'd expect it to perform poorly. But as the training set increases, maybe there's a lot gained, but then after a certain point, there's no longer anything gained. And so this is useful to figure out, like, what's the optimal training set size for whatever the problem domain is that we're looking at. So you can basically get an idea of how much data do you need, and it's not necessary to go beyond that for like any future training. And one problem that can affect our decision trees is the problem of overfitting. And so this is where our decision tree learns a hypothesis that's consistent, but it's using irrelevant attributes. So the attributes don't actually matter in terms of, say, like the general problem or future examples. So this results in these spurious distinctions, and it can end up influencing like decisions that your agent's making. So as you go through your decision tree, it's making decisions that are not appropriate at some point in the future when the decision tree is used, and that's because so like in the case of the decision tree, we would have detected the information gain, like an attribute that's not particularly important, was identified as being a good attribute early in the decision tree. So it's a closer to the root level when it should have been like just didn't matter at all, or didn't matter until very low in like one of the branches. So this is something that can really affect all sorts of learning algorithms. You just have like randomly distributed data, but it just, because of random luck, you end up with patterns that appear as if the selecting of the attribute has information gain. And so, yeah, all learning algorithms can be affected by this. And so something you have to watch out for, and maybe address with adjustments to your training data, or the size of your training data. And one interesting thing that you can do with D-tree learning is we can not just learn before the fact, like build a decision tree as part of the development process, and then that static decision tree gets, say, shipped with your game. We could have the decision tree actually have live learning in the game. And so the way that this would work is that we would have each of the decisions in the tree So those the nodes in the tree that are not leaves, but also the leaves. We will keep track of all of these examples. So what we had as that table form before, so like it looked like a spreadsheet. We're going to keep track of those example records at each of the decision nodes, and then also the leaves. And what this is going to allow us to do is, as new scenarios are encountered, well, we can still parse the tree that we have. So those new scenarios, they're going to have attributes, and they're going to be the same attributes that were used to build the tree up to the point that it currently exists. So we can parse through and then decide whether it reinforces the data we currently have, or whether some modification needs to be made to the tree. So this basically it's combining the D tree that we've seen before with the D tree learning algorithm. So again, that is mainly facilitated by putting the actual data from each of these scenarios is stored as part of the nodes of the tree. So any node in the tree can be asked to update itself given some new example, and then you can have these three different situations that play out. So this is from the Millington book. So if a node is a terminal node, and that means that in the decision tree that the terminal nodes are the nodes with the actions. So if that's the case, if the added example also shares the same action, then the example is added to the list of examples for that node. If the node is, again, this is the second one. If the node is a terminal node, but the example's action does not match, then we make the node into a decision and use the ID3 algorithm to determine the best split to make. So that means that we've added this new example, but it doesn't agree with what was uniform data previously. So now we have to, hopefully we have additional attributes to select from, and we'll pick whatever the best one, whatever has the best information gain, and then we'll do the split, or possibly more than one split depending on what the record was that was added. Now, if the node is not a terminal node, then it is already a decision. So this is like an inner node of the tree. We determine the best attribute to make the decision on, adding the new example to the current list. The best attribute is determined using the information gain metric as we did in ID3. So this results in, if the attribute returned is the same as the current attribute for the decision, and hopefully it will be, and most of the time it will be, then we determine which of the daughter nodes the new example gets mapped to, and we update the daughter node with the new example. But if the attribute returned is different, that means the new example makes a different decision optimal. And so this is where ID4 is the most painful. So because of that, if we change the decision at this point, then all the tree further down the current branch will be invalid. So you have to delete that whole tree from the current decision down, and then you have that whole pool or the whole set of examples again, and you have to do the entire ID3 using the current examples that you have. So if that happens, things can get rather messy. So this live learning decision tree the ID4 style, that was used in the game Black and White. I don't know how many students in the class are familiar with this game anymore. It's gotten pretty old at this point, but it was interesting. It was a game where it's I guess you call it a god game. So you are like overseeing a village, and so your job is to protect your village and help them to thrive and advance. And you have a pet monster type creature, this giant, and you could pick your giant, whichever you preferred of like one of three, I think. But your giant learned, and it was actually, it was kind of like a toddler, so he or she didn't know how to behave and just would randomly do things. And so you could punish or praise the creature. You like give rewards, and so like if the creature ate your own villagers, then you would give a punishment. But if it, say, stomped out a brush fire that would risk like burning up your village, then you would praise them. And so the creature would learn through this this feedback that you were giving what to do. And so all of the tree building and the adjustments would be based on these feedback measurements that were given. And so you get like these different values that were passed, and so then the tree could rebuild itself, and it actually it worked pretty well. You could pretty quickly train your creature. You had to make sure, you had to really focus on being consistent. Try to remember the way that you've been teaching your creature. You would want to make sure to try to balance out reward with punishment. Like you don't just want to punish all the time. But yeah, it would learn quickly to certain things that you did not allow it to do. Didn't always work so well when there were new novel situations. So you might have to intervene a lot if say some new disaster was occurring, for instance. You might have to intervene a bit. All right, so to wrap things up, we've seen how ID3 works, and so we have this nice general approach that we can use for some arbitrary set of attributes, as long as we've got enough example data for, say, selecting actions. And again, if we have all these attributes describing those actions, and we have good amount and quality of data that's consistent, then we can build our decision tree from it as like a pre-processing build step. And we can even have learning that's live by storing our records in our tree, and have a tree that's dynamically learning. So that is an interesting possibility there. Now there is a challenge in that. So like with the ID3, it's just too inefficient, especially for like online learning. And the ID4 approach, it works well when there it ends up not being a lot of changes to the tree. Like, so we saw the example, like worst case, if you have a decision node that gets flipped such that it no longer the best attribute is selected. So if you have that scenario, then you can quickly run into a performance problem. So it's not a completely fail-safe solution, and it's probably better suited for certain problems than others. But in the Millington book, he does say that from his use of it in some of the games he's worked on, it has worked pretty well, such that it will generally rarely have to rebuild parts of the tree. It can it still has that possibility though of getting unstable and just churning and churning and rewriting itself and hogging the processor. So yeah, this is the use of decision trees for learning is something that is a certainly a possibility that can be useful, and it definitely makes decision trees overall much more appealing as a possible use in video games. Hello. In this lecture, we are going to look at another topic in learning, and this is case-based reasoning. So case-based reasoning is one of the most popular AI techniques. It's up there with rule-based systems and machine learning. It has its origins from the symbolic era of AI, but it's really, I think, kind of identifies a shift towards the more machine learning techniques. Some aspects of case-based reasoning kind of have still grounded in symbolic AI, but also you're beginning to see this shift towards more machine learning type of approaches. So there's lots of commercial applications of case-based reasoning, and it's applicable to many domains, including video games, as we are going to see in this talk today. So first of all, I want to show just jump around a little bit in this video. This is just some academic examples of using case-based reasoning. I have the links in the lecture notes if you want to check them out. And of course, you can easily just Google or search on YouTube perhaps, and you can find lots of examples of using case-based reasoning in games. There's also a number of different papers. So researchers, including at Georgia Tech, have explored a lot of the utility of case-based reasoning and applying it towards interactive media, like storytelling and other sorts of like agent decisions. So yeah, it's worth outside of this lecture to check out some of these. Let's see if I can jump around a little bit here. Yeah, here's a case-based reasoning solution for playing Tetris with a good strategy to win. I think there's some like real-time strategy game examples. There's robot soccer, case-based reasoning. Some more strategy games here. So we're checking out, and we'll discuss a few applications as well. So with that said, let's talk a bit about, well, what exactly is case-based reasoning? So one of the classic examples with case-based reasoning, and this is, I believe, the first example that I learned about when I took an introductory AI class many years ago, is that we had a scenario for case-based reasoning applied to traffic planning. And so we've already learned about path planning. And so if we wanted to solve the problem of how to get cars to go where they need to go in the most efficient manner, well, we could just use a path planning system. And as we encounter new problems or issues, like a a road that's closed, we could just replan, meaning just rerun our A-star search again. And so this is going to work, but it's going to be as computationally as expensive as whatever the algorithm we're using is. And we might be able to optimize things a bit, maybe using a hierarchical approach to path planning could help. But if we were to use a case-based reasoning approach, then what we would be doing is storing previous cases, meaning on some other day, perhaps, a car might have wanted to go from point A to point B. And maybe that first time we do this, we would run our A-star search, commit to the computational costs of doing so. But then we store that record. We can store some features about this. We'll call it a case. So this particular case, we've got a starting point and a destination. We might also have other attributes of the scenario as well. We might store time of day, the weather, temperature, all sorts of things that could possibly be relevant and could be stored with the case. We could also omit information. We don't necessarily need everything. The key is we want to have enough information so that we can refer to this case in the future. So we store this case, and let's say in the future we again need the vehicle to find a route for going from point A to point B. Well, if we have some means of retrieving this record, so that means matching the current conditions to previously stored cases. So if we can find this record again, then we can find this cached path or the plan, and we might just be able to directly use it, or we might, if we can't find exactly the same case, we might find one that is fairly similar. So maybe rather than starting at point A, it's point C, but maybe point C is fairly close to A in terms of location. So instead, we're looking for a solution for point C to point B. We don't have it, but we can maybe still use that previously stored case for point A to point B. So maybe we can, rather than completely replan using A-star, maybe we can just add a little correction to this case. So some minor change to the previously defined case, and then we can try it out. And maybe we actually have the agent or the software we're using, it remembers what it's committed to in terms of selecting and using this modified case. And it might keep track of it and make sure, well, did the car actually get to point B? And if it does, then maybe we would update some metric of utility for this stored case. And we'd say, well, that case was useful. And so that can be stored in the case database. And we would know to use that case again in the future. We could also store the augmented case, the brand new case we made. So from point C to point B, we could store that as well. The idea is that with case-based reasoning, with enough cases, we will have sufficient data that whatever problems we face will be largely solved simply by retrieving an appropriate case, and then, if necessary, modifying that case to meet our needs. And so there is basically like a sequence of operations that we want to perform whenever we're considering like a case-based reasoning solution. Now, the different authors, different researchers have come up with slightly different terminology and processes. So it depends on what book you're reading or what papers you're reading, exactly how this works. But there tends to be a lot of similarity across these implementations. So you generally start off by analyzing the current situation. So that involves identifying some specific features of the environment and features that you know that you will find in your case database or case base. You then will retrieve the closest matching case or cases. You might actually grab multiple. At that point, you will adapt or revise of the cases that are found, and you want to make the case match the current situation. And as you can imagine, that's going to be highly domain or application specific of what it means to adapt. So like in our traffic example we just looked at, probably any of the modifications are going to involve using path planning and analyzing our map information or our graph data. So we might path plan a small section of the path, like add a little extra tail to the path in order to get the right starting point and end point in our path. But other problems where case-based reasoning are applied could be quite different in what it means to adapt. After this adaptation is made, there will be a test or review process, and ensuring that this modified case matches our situation. And if so, it's basically like a validation process. And if the testing identifies any issues, then we will repair it or perhaps abandon and try a different case. And then lastly, we will store the new case, the new solution in the database. And so the testing and the review phase, you might have this as something that like a process that can immediately be run, or you might have to actually simulate or wait for the real world results. So if you have a plan, wait for the plan to be executed, and then to find out the utility of the adaptation. So with case-based reasoning, it requires a good bit of domain knowledge in terms of authoring these different components in our case-based reasoning system. So, of course, the state representation, what information is relevant that is meaningful across all or most of the different scenarios that we're encountering. You don't want to be storing information about the state of the world if it's not an accurate reflection of the decision making. So that domain knowledge is important. There's also the design of a distance function. So this is the comparison of state representation across cases and the current situation. So what is the state representation of the current situation? And then we want to be able to have a well-defined function to find the distance between the current state and the state of all of the different cases stored in our case base. Adaptation is similarly something that is strongly influenced by the nature of the problem domain. So there's not like a universal adaptation that we could apply. And then same with the revision that you might need to perform. So all of these things really, it does require this domain knowledge. It also requires a lot of data to implement a case-based reasoning solution that is effective, meaning that the majority of problems that your case-based reasoning solution faces should involve simply selecting a case and then applying that possibly with some adaptation to the problem at hand. So not needing to like fall back to some other solution. So that means that you're going to have a broad coverage of likely scenarios. And if you don't have an exact match, you want to at least have cases that are close enough so that they're easy to adapt. So you're not making huge changes to the previous cases. You just ideally would be making just the right amount of change to them so that it is still easy from like an algorithmic perspective. And you have to watch out for the learning that can take place through this creating new cases, adapting and creating new cases, that the process can get stuck in a test and repair loop and not converge on an efficient solution. So something important to understand about case-based reasoning is that it is not a well-defined algorithm. You can't just quickly throw case-based reasoning at a problem. It is more of a methodology. So it's very high level, and it's modeling human reasoning and thinking, the same sort of process that a human might go through in terms of solving a problem, and that is, well, considering solutions that you've seen before and then adapting in that way. So the process is all about storing these past experiences, so these cases, and those are accessed in memory or the case base. So whenever you're given a new problem, again, you're going to be retrieving from this case base based on the assessment of similarity to current situation and whatever cases are being considered. And then reusing for the new problem, revising based on how well it worked. So this is determining the utility, and also remembering, saving this for future use. So the act of using the case-based reasoning solution is going to result in always learning because of whatever changes were made from previous cases. And even if you can use a case pretty much unmodified, you're still learning in the sense that you're keeping track of the utility or the efficacy of that particular case. So the cases that are in the cases in the case database that are most useful, they are going to sort of bubble to the top. They're going to be recognized by these metrics of like, if you have a certain case that you keep finding and it keeps being beneficial to generating new plans, then your case-based reasoning system is automatically going to favor continuing to use it until there's evidence that indicates otherwise. So we're reusing solutions to previous problems, and we have cases indexed by similar problem descriptions. So one way to think about it is that we have a problem space and a solution space, and there's a mapping between the two. So the problem space, we have a number of different problem definitions, and for some new problem that we haven't yet identified a solution for, we find a problem that is close within the problem space, and then we will figure out what sort of adaptation to make by recognizing the differences in the problem space, and that's going to inform us as to how different the solution is going to be in the solution space. Now, again, this is something that is going to be very application specific, but that's the idea, is that we will identify what those differences are of the closest matches of cases that we can find, and then figure out, well, what is this new solution, and then we'll of course store that. So here's an example demonstrating, kind of like from a human perspective, just a scenario where we might be applying our own sort of case-based reasoning. So this describes an example of, let's say, writing a or putting together a presentation. So you're probably not going to start from scratch. Often you might say pull a similar presentation. If you've given lots and lots of presentations, you're probably going to say, oh, well, I gave a talk that covered many of these concepts previously. So you might say grab a particular old presentation, and then rather than starting from scratch, you're going to be figuring out, well, how close is this to what I need? And it might be a perfect match. Maybe you've given the same lecture before, or you might maybe need to revise it, change it so that it's appropriate for the audience, or whatever the different conditions are this time. And so here you'll see where this process of revising can come into play. So we can, it makes sense in this situation that the author of the presentation can just review it, and they understand as they make these revisions if they're appropriate and accomplish the goal. So in some cases, there might not be a way to know other than just going and trying the plan. But in this case, the problem is appropriate, that like you don't have to give a bad presentation in front of the audience if you already understand the material. You can just sort of realize what problems there are. And so then this will introduce this iterative process. And so because of that, we will end up on an adapted version of the presentation that through some number of revisions, finally it is applicable. And then we could, of course, store it, save it to like the file system. And maybe also once the presentation's given, we can remember how the audience receives it. And then that will give us some intuition in the future on like if it's an appropriate case to select. So you can see how case-based reasoning kind of fits into this sort of human decision making, just as it does for a computer implementation. So here is another look at the case-based reasoning methodology. So like I said before, there's different authors have kind of refined and added or simplified steps to the methodology. But here you see you start with a problem. So you have a new case. So you're going to retrieve from previous cases and then perform the adaptation. Then, of course, this new case you can apply to your problem, or perhaps there is the revisions that occur and the retaining. So again, every time that you see case-based reasoning described, you might see slightly different presentation, but they tend to all involve at least the same core steps. So case-based reasoning is really built around the idea that similar problems have similar solutions. observations define a new problem. So these observations being, whatever the current state is, and then that will be used as an index into our case database to try to select our similar problems. So we really, that's critical, is being able to compute similarity in a consistent, accurate way, so that we can retrieve useful cases. Adaptation can be essential. We'll see that it's not always necessary, but certain problem domains, especially, adaptation can be important. So our case representation, like I said before, it's going to define or represent knowledge about the scenario that the previous case was generated, and we're going to use the current state with the selections of the same sorts of features. We're going to use that as a way to determine what are the closest cases. So the information we're going to store is the problem or situation. That's just like the definition of the problem. It's going to be domain specific. Then we're going to have our solution, which might be a plan, a classification. Again, this is going to be domain specific, the nature of the information that's being stored. And we're generally going to have an adequacy, and this is because we have lots of cases in our database, but when we find lots of close cases, we want to make sure we're using the best ones. And so one way we can do that is with this adequacy or utility score. And so this is something that's ever evolving. Every use of a case means that we have this opportunity to update it. So if it turned out to work well, we update it and have like a count. So we have a ratio like of successes relative to the total number of attempts to use it. So in terms of the information we have, it can be complete or partial. So for instance, like matching the problem description. We don't necessarily have to have all the information about the state of the world. In fact, in many cases, we probably prefer to not do so. We maybe can do just as well matching or indexing with less information. Similarly, the solution can be detailed or abstracted, and so the abstract solutions might actually be preferable for adaptation. For instance, if we already have an understanding of abstract solutions, then that would suggest that it's adaptable. So representation depends upon the domain or task, but we're going to, in terms of the way we'll store this is generally it's going to be like an attribute value vector or feature vector. So we just have a case represented by some number of features, and we could also perhaps have some kind of structured information rather than just like a flat vector. We could have something like a graph-like structure. That's, of course, going to introduce new complications for matching, for comparisons. And perhaps there's other solutions, but typically in video games, the feature vector approach is probably what you will see the most. I imagine maybe in, say, some strategy type games, you might have like a more of a graph structure, perhaps. But there's certainly, if you have efficiency on the mind, probably the vector is what you're likely to be working with. So the goal of similarity that we're trying to understand, the current state relative to cases. What are the cases most similar? So the goal of similarity is to select the cases that can be easily adapted or just directly used to solve a new problem. So this is basically it's a prediction of the utility of the case. And the utility is the measure of improvement in efficiency as a result of a body of knowledge. So it's basically how effective is a particular case at improving or being usable for our solution. So the similarity is something that we determine before we run or before we apply our solution, but the utility is something that we don't know until after the solution has been applied to the problem. So we won't know until we see if it works, basically. Now, there's lots of different ways we might go about computing similarity, but generally they will follow this sort of a pattern shown here on the slide, where similarity, the inputs is going to be the state, the current state of the world, so like maybe the feature vector, compared to the feature vector for the case. So we've got these two different state representations, current state and the state of the previous problem. And then for each of those features, we're going to do just a pairwise comparison individually. So we'll compare like the first feature with the first feature of the current state with the first feature of the case, and then the second feature, and so on. This similarity will often be normalized. And this is important because you want to have some understanding of how much a feature is influencing the similarity score. But that said, even if we say we normalize, there's maybe some kind of customized functions for each of the features. If we normalize that, say, to 0 to 1 scale, we then might actually want to have a bias that certain features are more important than others. So we also have a weight. So each of these individual feature similarities that are normalized will then multiply by a weight. So we'll have these weights that these could be determined through domain expertise. They could be just like the fact that we've identified the features are useful at all. We might further say some are more useful than others. We might also empirically determine these weights, maybe through some supplementary learning process in addition to the case-based reasoning. Maybe we find a way to optimize by making adjustments to the weights and the similarity over time. So that's certainly a possibility. And the similarity score is not something set in stone. There are definitely other ways, and we'll see other examples of similarity. But often you will see that this particular approach to similarity. So for the case retrieval, we've got our a problem description, and then we've got as input a collection of cases in addition to our problem, our current problem description. So the output of the case retrieval process is of this collection of cases, we want to pick the most similar case. And so that's going to be based on that similarity score that we just saw. And so this could be just the single most similar case, or we might, instead of just a single one, we might want multiple, because especially if we're considering adaptation, like maybe one of those cases is likely to be easier or better adapted than others. So it might be useful to have many. And another variation is that we simply just want a sufficiently similar case. And so this, you can imagine, might be useful depending on the nature of our database. It could have a huge number of records. We don't necessarily want to exhaust all possibilities finding the absolute best record. The cases that we do have, maybe the particular domain that we're working with, any case sufficiently close enough is appropriate for adaptation to the problem. So, and that can also improve the retrieval speed. So just simply having a threshold. So as soon as you find a case that is greater than the threshold, then that is acceptable. So in terms of solutions for retrieval, there, of course, you can simply just go through sequentially in the database and make a selection. And that, of course, the worst case, you'd have to search the entire database. You might have a two-step retrieval where you select a subset of cases and then sequentially within there, within that set. And so basically suggesting some type of strategy for a hierarchy. And there are also other more advanced approaches that we will look at briefly in a few slides here. Now, in terms of the features that we might choose to store in terms of representing the current state and the cases stored in our case database, like if you think from the perspective of, say, a video game, the state of the game world, there are features, what we call surface features, and these are just measurements from the state in unmodified form. So, for instance, we might have like just absolute positions of the agent and enemy. There's hardly any cost in retrieving that information. We have access to, say, a vector 3 XYZ position for the agent and the enemy, and we can just store that in the database. But for the particular type of problem we're trying to solve, it might make more sense to for some processing to take place. So we call these derived features. So derived features you can think of as like metrics. So these metrics are useful for the decision making. And you probably would have these same sorts of metrics would be important. Even if you weren't using case-based reasoning, other decision making that we've talked about so far in the class, you maybe still need these. So, but there are certainly implications of having derived features, and that is that they can be expensive to calculate. So you sort of have to balance things out. You might want to think carefully about, rather than just kind of blindly come up with, arbitrary derived features that you're not really sure about. You probably want to, spend some time thinking about it. Like consider, well, if other approaches or similar problems, what information would be useful, and then only spend the time calculating those if they're truly needed. So some features of our indexing that are desirable is one is that it be predictive of case relevance. So for like determining a similarity between the current state and something in our case database, it doesn't really matter how similar the feature vectors are if that is not a relevant case. Ideally, we would have designed the features that we're storing and the similarity score and the weights and so on, such that mathematically, when we calculate the similarity, that should be predictive of the relevance, but it isn't necessarily. So So that's something that you have to work to ensure that it works, like this mapping, this similarity um, is predictive of the case relevance. If it's not, then you're back to the drawing board and need to rework things. You also want this the indexing to be recognizable in the sense that it should be understandable um, why you're using certain features, and and also recognizing the matches from the cases, like recognizing why a particular case was selected. You also want the indexing to be abstract enough to allow for widening the future use of the case space. So if it's too narrow, then you're never going to be effective at adapting, and therefore the utility of cases will never increase, and the overall case base will not specialize in solving the problem. You'll just end up churning a lot of creating new cases that never stand out as being useful. Also, the indexing should be concrete. So discriminative enough to facilitate efficient and accurate retrieval. So here's another look at similarity measure. So this is using Euclidean distance. So you can think of your all of the features that define the problem space as each being a unique dimension, and you can use Euclidean distance for comparing, and but you still have that issue of before of some features might be weighted more highly than others if you're not careful. So for instance, if you say had like a distance in meters that varies a lot in terms of the different scenarios encountered in your game. So that would be like a huge difference. But if, say, for a bull, you had true or false, and it was a true value versus a false value is only different by, say, a 1.0. So if they're different, it's 1.0. If they're the same, it's a difference of 0. So compared to, let's say, your distance in meters, the Boolean would be weighted very small compared to these potentially huge distances. So you'll need to make sure to normalize these. But then, in terms of importance to the problem, you can have weights, and so even if you're using like a Euclidean distance, you might have weights applied to the difference between each of these features. All right, so here is an example from a particular game. This was actually, I believe that this was like a reverse engineered StarCraft agent. So there's I guess like some hooks that you can monitor the StarCraft game while it's playing. And so you can input user inputs and also read out the positions of enemies and your own units. And so you can have an agent that plays the game. And so this particular authors, they made a case-based reasoning solution to playing the game. And so what it was looking at was for selecting strategies that were based on what types of units were present. And so this makes sense because, like, say you have a lot of aerial units, then you're going to need aerial meaning like flying units. In real-time strategy games, that often means that you have to have really specialized defensive units for protection, like ground to air sort of attack or other aerial units. So and then you can also have other sorts of strategic situations where you have to have specialized units or configurations of like formations. So you could have a case-based reasoning solution like was developed here. The important thing for similarity of the situation was the ratio of troops. So you can imagine if you tried to represent this with like absolute values in the similarity score, that would put a huge burden on the case-based reasoning or the database for case-based reasoning to represent all of these different absolute value amounts of, say, ground troops and aerial units and long-range indirect attack and all the different possibilities. But by representing state with simply the ratios, that added a generalizable element to the similarity scores, and so the learning could take place more easily. So yeah, you have these ratios, and then that leads to the different strategies for what's appropriate for production. So like building new units to get the correct strategy or to support the correct strategy, which would be to like be able to defend your base from aerial units or long range ground attack or whatever is appropriate. Now, another approach to retrieval that can be used is a KD tree. And so this is one of the more advanced approaches that can be used. So you can imagine that we could do the sequential approach, like I mentioned before. You have your case base, and you just compare your similarity score to all the records. If you're looking for like the best one, you have to look at all of them. But we could come up with some hierarchy, and that's what a KD tree allows you to do. And so if you think of your feature vector that represents the state of the current problem in the previous cases, if you think of that feature vector as like a multi-dimensional vector, then you can apply the KD tree. And what it does is you analyze all the dimensions, and you pick one of the dimensions, and then you see if there is a threshold value that you can use for like greater than or less than, and split all of your data points. In this case, it's the cases in your database. So if you can put like roughly half the cases on the left and half the cases on the right, splitting on that dimension, then you've taken the first step in creating a tree structure. And then you can further split, selecting whatever dimension does the best job of splitting. And you can just keep doing that, and maybe returning again to the same previously used dimension. And so you keep doing that, and if you optimally select the split points and the dimensions for the splitting, you will end up with a roughly balanced tree. And so then for calculating similarity or selecting similar records, you now have this mechanism for analyzing the current state, the current problem state, and you just go through comparing the appropriate dimension at each node to the threshold value, and you can work your way down, and then you can find the best match node. And so this is fairly popular to use in case-based reasoning when you want efficient retrieval. Now, you might also consider using some sort of dimensional reduction strategy. And this can be useful because when you do select a whole bunch of features for your case storage, some of those features might turn out to actually be redundant. They're highly correlated, and so they don't really provide much contribution to differentiating cases. You could have maybe just used one. And that might be something that would be reflected like in your weights, especially if you can figure those out yourself. But you might get to the point where some features are weighted so low that you don't even need them. But we could maybe formalize that process doing some sort of dimensional reduction, like a principal component analysis sort of approach, and then that would help us have a better designed set of features, and also or potentially the weights, or just revising the whole strategy. What do we even need to store as our features? So now our typical retrieval of records in the case space is built around finding the closest example. So if we're going through sequentially, we'll just keep track, sorted order, which ones are the closest, and we might pick the K most similar items. The problem is, in doing so, we might end up with a lot of cases that are all very similar. So it doesn't really matter which of any of those that are selected for adaptation or to apply to the problem. They're all going to have end up having similar utility. But if we're trying to promote learning, then we might actually want a more diverse set of matches. So this is where this concept of diversity enhancement retrieval comes in, and so there's a lot of research that's gone into applied to case-based reasoning, is trying to improve on this problem that I just described. So selecting K items such that they are both similar to the current query but different from each other. So we might need to modify just solely picking what's the closest to the current problem description. But as we are, say, maybe we select the closest problem, then that's going to augment how we're going to select, like, say, the next item as we work our way up to K total items. So we might be forced to look further away from the original problem in a methodical sort of way. But then the benefit is we get a broader coverage of the possibilities, and we're also we can avoid some of the less relevant items that maybe are redundant with another case that already has high utility. So this can be very useful for case-based reasoning. So in terms of case adaptation, this is an area that, again, is very domain specific, and it's very much an open problem because there's not really there's not a universal way to adapt cases. In some cases, in some situations, you might be able to do things kind of symbolically. So you might recall in our look at rule-based systems, we had like wildcards and were able to manipulate symbols in terms of analyzing problems. So in some cases, you might be able to do that, to be able to, say, identify certain symbols in your cases and just be able to swap them out with a new symbol, and things will work appropriately. But it'll depend on the problem. But here's an example of like a recommendation system. Say you're searching to buy a new used car. So this gives an example of maybe the user identifies some features that they're looking for, and a previous successful match that like led to a sale is found, but it has some differences. So you might go through, say, some like wildcard swapping, maybe related to engine features or color, that sort of thing. And so you could maybe identify some adaptations that could be applied to a previously successful match, and then you would have to go through some maybe validating. So for instance, you might do the variable swap approach, but then you generate something that's just impossible, like engine configuration would never, like a V8 would never have a certain number of valves, or displacement would just be impossible. So you might have to have some sort of like additional watchdog or validation that would go through and confirm that the adaptations are appropriate before attempting to use them. But assuming that you can come up with adaptation that works, we can understand the benefit that adaptation can give us if you think in terms of if you don't have good adaptation, like if you don't have it at all, that means you're going to have to store more and more cases. Because your database has to be bigger because you're not adapting. If you do adapt, that means your database can be smaller, and therefore retrieval effort would be lower. So you can consider this trade-off as you go from a few cases to many cases. The more cases you need that are appropriate for the problem space, the retrieval effort is going to increase linearly. But for adaptation, if you have a few cases, that means that it's going to be harder to adapt generally, that because your case is going to be further from the solution. So any sort of algorithm that you implement is probably going to have to work harder. But as you add more and more cases, that means the difference or the distance between like a previously stored case and whatever change needs to be made so that it's applicable to the current problem, that's going to get smaller and smaller. So there's a sweet spot where the retrieval effort and the adaptation effort hits like an optimal point. And so this is all kind of idealized. This isn't based on real data. This is more like just trying to give you some intuition about why it's useful to have adaptation. That said, it's often hard to have adaptation in games, and many of the examples that you find, including the ones I'm showing you, have no or minimal adaptation. So the adaptations that you have, again, they're going to vary a lot depending on the domain. So we've talked a bit about how the adaptations might be generated. So you might have structural adaptations This is where you have adaptation rules applied directly to the solution. So maybe modifying certain parameters, swapping out or interpolating. So that's much like what we're looking at or considering with the used car sale example. But you can also have derivational adaptation. This is where you reuse algorithms that were maybe used originally to generate the case solutions. So this would be like the classic traffic planning example. So you're going to reuse the same algorithms that you used before for path planning, and those results were stored as cases, but we might use, say, A star to, so we got the path from A to B, and now we need C to B, then we would find a path from C to A added to A to B, so CAB. So all we have to do is that little bit of extra path planning for C to A for our start location and then destination. So again, this is all going to be domain specific as to whether it's appropriate to have the structural or derivational or maybe a combination, or maybe you just don't need adaptation at all for your solution. So yeah, I've already mentioned that there's no good general adaptation strategy that you can broadly apply. It's really going to require some expert design for your heuristics and your constraints. All right, so let's look at an example here. So this is another real-time strategy game. So Wargus, I believe this is like a clone of your Warcraft 2 type or StarCraft type of game. And so these authors developed a case-based reasoning solution. And so this game involves resource gathering and building like in Warcraft 2. And there is a building specific state lattice that is in the game. So these nodes represent different states that, say, a particular player, the commander of the forces, what the capabilities are. So you're probably familiar with this if you played a real-time strategy. Like, you have to build certain buildings that allow you to build new buildings, that allow you to build new units, and those new units might allow you to collect new resources, and then you can build another type of building. And so you have this chain of dependencies that defines what you can do at any given point. So in this particular case-based reasoning implementation, the agent has some particular state based on what has been built, and this will open up different tactics for the agent. So as things get built, it might identify a plan to build more stuff because, like, your army is not advanced enough yet, so you need to build more things. Or it might be that the current situation, you have a certain set of buildings built and resources available. So that opens up certain strategies, like maybe for setting up protective turrets or putting together a military force to go and attack. And so in this example, they used a k nearest neighbor matching. And so in this case, the different states of the world and the states, the feature vector stored in the database, case database, and reflective of the current state of the game, those features were related to the state lattice, this hierarchy, and maybe other features, but they're all associated with a plan which is repeated many times in the database. So you've got like say a strategy of attacking or defending, or maybe different specialized types of attack and defending or building. So these different strategies appear more than once under different scenarios represented in the cases. And so that is because of that sort of unique situation with these sort of redundant outcomes or the plans. The k-nearest neighbor worked well. And so with k-nearest neighbor, what you're doing is, so if you have some means of measuring distance, you can find the k-nearest of something. So we could use our similarity score that we've talked about before. But in terms of selecting a case, what we're actually doing is multiple cases are determining the outcome, and that's the majority consensus. And that, so of the k-nearest cases that we find in the case database, the assumption is that we'll find lots of cases that all point to the same strategy. So like several will say like a particular defensive strategy or an attack strategy or a building strategy. So we'll have different unique cases, but they all will point to common solutions or strategies. So we can just count up of those k-nearest. Well, what is the dominant feature strategy? And so that decides, in this case, that's the deciding factor for what will the case-based reasoning solution selects. So going back again to the slide, so that there's no adaptation here. The only revisions that are made are it's just updating the utility scores. So those cases that contribute to the majority, we update their performance results. All right, so another one that this is another real-time strategy game, and so this is an application building a plan. So we have the case-based reasoning coupled with these fairly complicated plans. So rather than having one large elaborate state machine, we have these snippets of plans. So it's a little bit, it's got some elements of like A-star planning that we've talked about previously, but the case-based reasoning is identifying from the current state of the world these pieces of plans that can be applied and expanded and executed. So we can build on previous plans by like appending to whatever the agent is currently executing these new bits of plans. And so we can update periodically, adding this. So another example, this is a commercial application. It's probably one of the most interesting examples of case-based reasoning that I've seen in video games, at least. And so this, you may be familiar with it. This is from the fighting game Killer Instinct. So I'm showing a little bit of gameplay here. I got this, a fan of the game recorded this to YouTube. And so he's demonstrating training his own agent. So in a way, he's programming it through example. And so he is in control, human control of the agent that he's training. And so what's going to happen, these are called shadows. So he's training his shadow how to fight this particular enemy. And then later he can pit his agent against the other agent. And so you can either fight the built-in AI of the game, or you can fight other, like your friends. And so you don't have to actively do anything during the battle. You just sit back and watch. But all the move selection is based on a case space that is built of the human trainer's moves. So in fighting games, there's a lot of high level strategy, such as trying to like uh, trick the opponent into responding to thinking like a certain attack is going to happen that it doesn't, or say forcing the opponent to stay at a certain range, stay far enough away. There are things you can do to try to set up the opponent to get in the right spot so you can get a combination of moves going. And there's certain combinations that are really hard to stop once they start. And they can do a lot of damage. So there's lots of high level strategy, but there's also the sort of reactive type of things that a player might do as well. So high level strategy might involve lots of steps, like a build up, say the setup to get a combo, or the actual execution of a combo. You can think of as a high level strategy. But there's also just individual like reactive sorts of moves that are important as well, like blocking if there is an attack that is coming. So it is really a challenge. How do you get like case-based reasoning to capture not only this sort of reactive response, like a immediate reactive decision making, but also the high level strategy. So in Killer Instinct, they of course have a case database, and they've got 40 state variables that, and these cases are stored on a really short time interval. So it's on the order of like per frame or close to it of the game. So the state information is things like whether the player is on the ground, or sorry, the character is on the ground or in the air. And again, the training data, all the state information for the training data, this is coming from a human playing in this little special training room, training arena, I guess. There's some information that is character specific. So like if a certain character, say, can do special moves that no other character can do, then you might have information about that. There are also locations of items, and in addition to like where the opponent is and what state they're in. You also have, like, say, if there's a fireball or a projectile flying through the air, there's information about that. Animations, where they are in their frame count, is stored. Previous action is also stored. This gives some context to any of the cases and is useful for chaining together multiple cases. So that gets back to the high level strategy that we were talking about before, is that by being able to relate one case to the next allows for having these sequences across time through multiple cases. Actions taken, of course, that's the what we're looking for is for any given state, we want to know, well, what's the appropriate action to take. So these cases are stored in a feature vector, very efficient, like compressed, and designed for fast matches, and then a nearest neighbor is used for retrieval. So in terms of adaptation, there's almost no adaptation like the other game examples that we've seen. There can be some small changes. I believe it mentioned that they can swap like one character for another when there's lacking data. So like if your agent has been trained largely on certain opponents, and then there's say a new opponent, it can just make assumptions that, well, it's going to be like some other opponent, even though that's not going to be a perfect match. And it's not going to learn from this. The only learning takes place when the human trains it. So that's one thing you're going to lose out on, or at least I think it doesn't adapt other than the human. I guess potentially it could, similar to the way that the human training works, but I don't think they do that. Not positive though. All right, so oh, and by the way, if you're interested in more information about the Killer Instinct, I'll have notes about, so that there's a game developer conference presentation. So I believe got a link to a full 1 hour talk on that, and then also a game developer conference paper that's on the website that you can check out if you're interested in seeing more details about this. So yeah, and I think that is probably the best example of case-based reasoning, certainly with commercial games. All right, so we will conclude by looking at advantages of case-based reasoning. So big advantages, the learning potential. This reduces knowledge acquisition effort. It requires less maintenance to like maintain good solutions with your agent. You have this ability to reuse solutions and improve the problem-solving performance. You can make use of existing data that you might have. It improves over time. It's adapting to changes there, so incremental learning is actually taking place. It's suitable for complex problems lacking formalized models. So you don't necessarily have to have some well-defined model. You might just, potentially you might not even have strong expertise in the problem, and you might still have success with the case-based reasoning solution. You also have an audit trail. You know the cases that led to solutions, and that can be useful. Maybe less so in video games, but in general is useful from an AI application sense. Also, case-based reasoning has been well accepted in various application areas. Certainly, it has worked well in like the game examples that I showed, and also other areas as well. As for disadvantages, you can quickly end up with large databases. These databases can be challenging to scale, especially as you face a bigger and bigger challenge of retrieval and maintaining the information in the database. It can be difficult to change problem domains. It's like basically, even though you might have a good understanding of how the methodology of case-based reasoning works, it can be difficult to say reapply a implemented system, or say you have an existing case-based reasoning solution in a database that's full, but the problem changes substantially in some way, like new maps, or for like a video game, maybe you introduce a bunch of new maps, and so you still have all the old database. So that even that can cause trouble. So like the differences might be bigger than whatever your adaptation solution is can adjust to effectively. Case-based reasoning also can have problems with data noise. So you can end up with poor matching, or noise ends up where where you end up storing lots of records because they are different. Where if you didn't have that noise, like you maybe would have had closer matches, and you wouldn't be storing as much to the database. But so the noise is basically creating these kind of false new cases. Also, case-based reasoning. A lot of like the non-video game solutions are not fully automatic. Been a lot of use of like human intervention. So the case-based reasoning will, if it doesn't have a perfect match for a solution, it'll ask a human to intervene somehow to maybe make a final selection or adaptation, or say that it just the system doesn't know, so the human has to add the new case. Well, that's not going to work in a video game typically. I mean, I guess there might be a few special cases in video games where that would, but ideally in a video game you want it completely automated, and case-based reasoning isn't necessarily going to be easy to always do that. If there's holes, if there's things missing in terms of the case base. And last thing to mention, this is from the old website, aigamedev.com. This was a little a critique of case-based reasoning for game dev. And so this quote, in fact, the crux of the argument, if you have a good scripting language or even a visual tree editor to capture sequences, you'll be orders of magnitude more productive and more reliable than an expert trying indirectly to get the system to induce specific sequences from examples. As such, it's fair to claim that case-based reasoning isn't particularly well suited to these kinds of problems in game AI. So this is really the author has issue with the fact that case-based reasoning only has these snapshots, and it can really be a challenge to get snapshots to be identified and selected in the right order so that you recapture these sequences, but still allow for diverse sort of response to changing conditions. So yeah, that's our look at case-based reasoning. It is something that I think in certain domains, even within video game genres, that case-based reasoning could be effective. Certainly the fighting game scenario has been proven to work well. And I think also examples in strategy, maybe strategy game type genres, real-time strategies or turn-based. And it might be a supplement to other AI approaches, not to be like the entirety of the agent implementation would be a case-based reasoning solution, but maybe something to augment other approaches. Hello. In this lecture, we are going to look at n-grams. This is a technique that you can use for agents to learn what a human player is going to do based on their previous behavior, especially in terms of analyzing sequences of behaviors and looking for patterns. All right, so it's all about action prediction. And so this particular technique with n-grams is especially popular with melee combat games. So these are like your fighting games such as Street Fighter, and you have lots and lots of high frequency of actions being performed by the game player. So pressing like the punch and the kick buttons. In fact, in many cases, the action prediction is directly related to user inputs. So just those are the sample points. Now you might evaluate some higher level actions performed by the player. So for instance, you could, instead of the raw key presses that you're trying to predict, you might use something else, such as say like Street Fighter 2 throwing a fireball. So that actually involves a combination of key presses, but you could treat the action selection as being just the fireball rather than the arrow key manipulations and then the punch button that's used in combination. So this can also be used for any other types of decisions that players might use. So like, where does a player choose to go? Maybe down a particular hallway in a multiplayer game. If there is an intersection, you could apply this to weapon selection. So maybe the agent trying to guess what weapon they're going to be attacked with next. Some sort of tactics. There's lots of possibilities. Millington mentions in his book that this particular technique is so heavily associated with melee combat that a lot of game developers don't even consider using it for anything else. But in fact, that it can be very useful for other scenarios, and being a fairly straightforward thing to implement, that they might be missing out by not using it. So the whole approach of action prediction as applied to humans is something that really relies on the fact that humans are bad at being random. So if you ask an individual to intentionally select random choices, they will tend to make choices that focus on change rather than correctly understanding a random distribution. So for instance, if you have two choices to make, you'll tend to have an individual will have a preference for changing whatever they did before. So if they hit the A button, they're very likely the next time to hit the B button, even though in a true random distribution, there's equal likelihood of A or B being selected. So you will tend to see an absence of repeated values in a sequence when you analyze when a human's performing it. They also forget over a short period of time what patterns they have followed before, and because of that, will repeat those same patterns over and over. Furthermore, a single individual, you might think, okay, well, it'll be easy to learn one individual, but that can actually have carryover for applying that same knowledge against other human opponents. So Millington, I have a quote from Millington here. We have shared characteristics that run so deep that learning to anticipate one player's actions can often lead to better play against a completely different player. So that means that you can have offline training. You can train on, say, some small number of human opponents, and then you can have that agent with that the training data applied to create its decision-making algorithm. So applying that same understanding of human behavior for some small number of human players, and it'll carry over to successes against other human players that were not trained on, just because of this tendency to for all humans to kind of make the same sorts of flaws in their decision making. So let's start off by looking at a naive algorithm. So this is not going to be the Ngram algorithm, but will start to get us thinking in the right direction here. So we are going to try to predict what the human player is going to do just by tracking the frequency of their choices. And so we could just keep a running number of whatever the choices are. So we know there's a total count of all choices made, but then some portion of those is going to be like choice A, and some portion will be choice B. Of course, if there's further choices, it would all be divvied up. But these ratios relative to the total, like the number of A choices over total choices plus number of B choices over total choices, and so on, that the sum will add up to 1. So once you have that sort of information, the idea is that the agent could just say, well, I'm going to guess the player is going to do the thing that they've previously done the most. So if one key press is more common than another key press in, say, a fighting game, so like maybe the human player throws a punch a lot, then the agent can make a selection that says, well, all right, they punch more than anything else, so the agent will make a selection of their own action with that assumption. So it might be that they block high, or that they counterattack with a low kick, for instance. Now, the problem with this approach is that it gives a lot of feedback to the player. So the human player immediately knows what the agent is doing, and they'll realize that if they punch a lot more than anything else, that they start to see the agent performing clear counters to that. So that is knowledge that the player is gaining. And they will begin to experiment and learn, and they'll realize that they can alternate, for instance, wait until the agent catches on and then switch, or just generally alternating can be beneficial, or otherwise balancing out their strategies, but not necessarily avoiding patterns in the their strategy otherwise. Now you can implement this. Probably the most naive would just be to keep an indefinite tally going. So you're just counting all occurrences of punches and kicks. Now you could add the ability for the agent to be able to more quickly change the observed statistics for determining these probabilities. So you can imagine, if you keep an indefinite tally, the longer you observe the player, that it's going to take that much more new observations before you can shift the ratio, because you're gonna have to have counted so many observations to shift the ratio one way or the other. But instead of counting from the very beginning, the very first observation on forever, you could instead have a sliding window. And this would typically be implemented with a circular buffer. Though you could also use an exponential moving average, which doesn't involve any memory storage other than a single value. But with the sliding window, you have a circular buffer, and so at first you just treat it like a regular array with empty slots, and so you keep a count of how many slots are used. Then once the circular buffer is full, then you have to go to a replacement strategy. So anytime you want to add new data to the circular buffer, you remove the oldest and replace the oldest value with the new value. And so at that point, anytime you're adding new data, you're removing old data, and you typically couple this with a running total of what's in the array. So when it's time to add something to an already full circular buffer, you subtract out the oldest value from the running total, and then you add in the new running total. And of course, you know the count of values in the array. So from that, you can quickly compute the mean or the average. So this improves the naive algorithm a little bit in that it can more quickly adapt. The learned probability can change more quickly, so it's not going to get slower and slower at learning. It'll at least be able to learn, but this still doesn't solve the issue of the human player sort of figuring out an exploit to the agent implementation. So we can imagine for these scenarios that we're talking about, that we're trying to learn the player choices. We can imagine just a simple game. We'll use the left or right hand game. So this is where you show your opponent an object that you are going to conceal in either your left or right hand. So you put your two hands behind your back. You pick one of the hands to put the object in, squeeze your hands tight, and then bring them to the front of you, and then you let the opponent pick. And they try to pick which hand holds the object. And you could repeat this over and over, which is what we're proposing here. So the agent is either picking left or right, and then the result is the hand opens that they choose, and you either see the object and know you got it right, in which case clearly you know which hand has the object, or it's an empty hand, but you also know what the answer is. So in either case, it's being revealed to you which hand actually had the object. So the agent can observe this information. Now, again, that we could use the naive algorithm either with a running total from the beginning or with a sliding window. Or what we might do is just keep a history. And so we can think of this history as a string of symbols. These symbols being like either an L for left or an R for right. So in this string, we have a history. And one thing we might consider doing is to make a prediction based on the recent history that we're observing. So for instance, if the player that's hiding the object in their hand, the last two times has hidden the object in their right hand, well, that gives us a window size of 2 that we're considering. So we might then go through our history and find an occurrence of right. And then we could just pick, well, once we found the position of right, well, what comes next? So we could just look in the history and pick one. And then that third character in the sequence, or whatever comes next after RR, that will be our guess. Now, this is rarely used in video games as a way to track the human behavior. And usually this is instead done in a sort of a table form, which we'll look at. But you might imagine, well, it would probably be more reliable rather than just searching for the first occurrence of right. We might actually want to find all the occurrences of right and what comes after it, and then determine a probability based on the possibilities for what we've seen before. So if we see right, left, a very high percentage, like let's say 80% of the time you see right, left, then that's what you would want to pick is left. But you might have some other probability as well. So either you're going to have, in this case of the scenario we're considering, you're either going to have a left or a right. So maybe the human does a good job of evenly spreading out the left and right occurrences for that particular sequence, but maybe not for other sequences. So this gives you the basic idea of how the Ngram works. at least from a high level. But rather than keep this history as this long string and constantly analyzing it through these search operations, it would probably be better if we can make a table. And if we're sticking with this window size of like 2 choices, and then considering what's the third, well, we can build a table like what's shown here on the screen. So this will allow us to keep track of probabilities. So we can update our probabilities based on what we've observed in the history. So we need to consider all the combinations of 2. So if our window size is 2, then this is called a 3-gram in this case. So that's where the n-gram comes from. Is whatever your window size is plus 1 is what you call the gram. So 3 gram in this case. So we want to just make a lookup table of these probabilities. So if we see about an equal split with left, right versus left, left, then you would just have like 50% probability stored for each of those. But maybe for, say, right, left, and right, left, there's a heavy bias. So that's clearly something that the agent could take advantage of and do better than chance in terms of guessing what the human player will do. So you want the table, of course, it's going to need to sum to 1 because it needs to cover all possibilities, and you want to make sure that you've properly generated the combinations of choices, whatever your window size is. So so this would be great if we could analyze, say, our string and then populate these tables. But we could actually use a table structure like this to tabulate on the fly what the probabilities should be. So we can make a little modification. Rather than storing probabilities as the cells in our table, we can instead store the count for each intersection of the rows and columns. So we know that, say, for occurrences of the previous 2 choices by the player is left, then we find an intersection with either right or left. Once we observe that third key or third choice made, then we just update a tally. So if we get a left, right, well, we're going to, if you see my mouse cursor here in the video, we are going to just add to this value here. If we see a right, left, well, we'll find right in the table and then in the row, and then we'll look for the column left. So right, left is here, and so we'll add 1 there. Simultaneously, we are also keeping track for each row 1 value. So it doesn't matter how many columns there are, there's still going to be this 1 value, and that's the running total. So this running total value allows us to quickly determine our probabilities. We simply will need to just perform a division. So we can, anytime there's a table lookup or anytime there's a need to make a prediction, we do a table lookup. So we know what the previous history is. We don't know yet what the player is going to do. So the idea is we would make the prediction like right before the human player does something. And so we look at the recent history. We would see, well, they just hit right, or made the choice right. So what's going to come next? So we look in the row, and then we find the biggest running tally, and that's our selection. And if we actually needed the probability for some reason, we could perform the division. So that is basically how n-grams work. Of course, the thing that you need to decide when you're designing this solution yourself is, well, what should the window size be? So how do you get to where you have a window size? Because you can imagine you could pick two or three, or you keep going, maybe 10. Um, and so you could test empirically, just have a number of people play the game and analyze and see, well, what is occurring the the most, and furthermore look for the accuracy of these choices. So you could sort of aggregate all the data and figure out how that compares to, well, what if the choice was random? So if the human player is truly random, then with two choices, you would expect that if you're making a guess as to what comes next, then you would have a 50% chance of getting it right because the human player is doing such a good job. So you could actually just test out all of these different window sizes and then pick which one does the best job for accurately predicting the player. Of course, you're with two choices, you're looking for better than 50%, and you want to pick the best of all the possibilities. So you probably will find that the window size will be around 4 or 5, and that is the sweet spot for a human player typically. Once you start getting beyond that 4 or 5 range, you're gonna start having a quick drop off of performance, and that's because a human, when they're just trying to make up choices in their head, intentionally trying to be random, they're going to change what they do because of these short causal processes. So there's a lot of things that can play into what the player is doing, but these tend to occur over relatively short ranges of time. So like no one will tend to plan out something and then follow through that plan for a very long period. There'd be some interruption most likely, or they're just not thinking that far ahead, and therefore they're going to be driven more by like the environment in the game based on what their next choices are going to be. So there's again a sweet spot for where the most predictable patterns of behavior will occur, and so that's what your agent should shoot for, and probably you get your best luck by doing something exactly like what's shown in this table. You'll just test it out and see how well the different window sizes work in terms of your selection, and then you, of course, pick the best one. But one thing you can do to improve on the n-gram concept is you can just use a whole bunch of window sizes all at once. So that's called the hierarchical n-gram, and this can work really well for online learning. So the way it works is that you can have small windows and large windows that you're populating all of them in terms of your running tally. The question is, well, which one do you pick? So you've got say with a hierarchical 3 gram, you have 1, 2, 3 levels. You could pick something else as well, and you would have all the different possible n-gram sizes below that. So again, which one do you pick? And so you might imagine with the larger n-grams, they're going to be more accurate up to a point. So you probably wouldn't go much more than say 5 or 6 as your size, but it's going to take a lot more data before you can really make an informed decision with the larger n-gram sizes. The smaller n-gram sizes, you're going to get your data very quickly just because there's less possible combinations that can occur. So the idea is that you might start off with your hierarchical n-gram with no information, and you begin to observe the opponent human player. So in that case, what you're doing is you, in order to decide which of the n-grams to use for the prediction, well, which one has sufficient examples? So, and you might basically be looking at the rows, not necessarily the whole table. Would you need the information? But say per row, you look to see, well, is there enough information there? And then so these might be just empirically defined thresholds to be sufficient. And once you have reached that threshold, then it becomes a candidate for consideration. And so you look up in each table each table row that does have sufficient examples, you look them up, and then so you say a particular sequence that you're looking at. So you might be looking for, say, left, left, left. So in your 1 gram, you'd be just looking at one back, so that'd be left. It would be the row you look at. But 2 gram, you'd be looking at left, left, and 3 gram, you'd be looking at left, left, left. So you might find that, say, you have entries for the 1 gram and the 2 gram, but the 3 gram doesn't have sufficient examples. So you don't even consider the 3 gram. So it would just be between the 1 and the 2. Then what you do is you look at, for that row and the possible choices, is there a clear winner? So like whichever entry has the highest value. And so if, say, the 2 gram has a higher value prediction, like guessing, say, right, and it thinks that there's an 80% chance that there's going to be a right, but the 1 gram only has the max is a 60% chance of left. Well, you would want to go, in this case, you would want to go with the 2 gram that has the higher likelihood predictive accuracy. And so you're still going to be updating the tallies for all of your tables. And so when you're learning very early on, you're going to rely more on the smaller n-grams. Then you're going to start to specialize or observe specialization in your tables, so that for maybe some certain sequences, it'll be highly predictive for any of the different n-grams that you are tracking. And that is going to probably be related to the strategy of the human player. Maybe there are a very highly repeated sequence that maybe is a longer sequence that this just related to some activity that the player is performing, whereas other cases they're making more like shorter decisions, and so therefore you would want to use the smaller size n-grams, and again, it's gonna, you just wait for it to show up in the table. And And then of course you'll have to take longer to learn and not get sufficient examples to use those larger size n-grams. So the algorithm sort of smoothly improves over time. Just once you have the data, it can start making more informed decisions. So it's a pretty powerful technique. In fact, it ends up being so effective that in many cases, AI designers actually have to dumb down the implementation. It works just that well, especially in fighting games. So you can make the AI where it is basically unbeatable for a human player. They don't realize they're that predictable, and the agent can just really take advantage of them. So you might intentionally avoid picking the best choice always, maybe intentionally throwing in a poor choice, maybe control with difficulty settings, which n-gram settings or errors in responses are made. So yeah, this is certainly very useful. It again can be applied to different types of gameplay decisions, like we mentioned before, weapon selection, locations that the human player might visit. You also see this technique used outside of like game AI, and it has other applications that it is useful in as well, such as language learning, where different phonemes fall in like the likelihood, and then that can inform other parts of, say, natural language processing. So if you're trying to figure out some ambiguous syllable sound, well, you can make a guess because well, what's the most likely sequence of, say, 3 syllables in a row, for instance. So definitely this is an algorithm that you should keep in mind if you're developing an agent that is working against a human player, and that where it would be useful to know what's the next action that the human player is going to pick. Hello. In this lecture, we are going to look at naive Bayes classifiers. So this is a way to conditionally determine what an appropriate action for an agent is to take that will be informed by human provided training data. So we're able to actually learn to replicate the human decisions just by analyzing what has been done previously. So naive Bayes classifiers are a simple learning strategy based on statistical analysis of reference behavior. And it's built on 2 concepts. The first is, what is the probability of an action being taken given the current state? So this might be something like in a race car scenario, what's the probability of braking if the distance to the next corner is near and the car is going fast? So we might have a lot of previous examples from a human demonstrator, and be able to leverage that data to make this determination. And the other thing that naive Bayes classifiers relies upon is that if you have more than one feature in the current state that you're using for conditional determination of the action being taken, like braking, then those are naively considered to be independent. So in the example just given of the race car, you assume that the corner is near measurement is independent of the going fast measurement. So we will need data from a human player, and we'll have lots and lots of examples of different points during which the human is performing their decision making. And so in this case, one of the decisions that a human driving a car would make is when to brake. And so we can either be pressing the brake button or not. And we have different world state that might be considered. And so in this case, we have distance to the next corner and speed in this particular table. So just looking at this, it's kind of hard to interpret. You have a lot of floating point number values and many different examples. So it's hard to work with in its current form. So it'd be nice to try to simplify it in some way, and that'll also help with our Bayes classifying. So one thing we could do is somewhat similar to fuzzy logic, is to have categories for the distances and speeds. In this case, we would maybe pick a threshold for two different states, for near and far. So any distance that's less than the threshold will be considered near, and any distance greater than the threshold will be considered far. Same thing with slow and fast with the speeds. Now we could potentially have additional categories as well, and it'll really depend on the problem, how many different states that we would want for this discretized representation. But if we can make it so that it's easy for a human to understand, then it'll probably also work well for the naive Bayes classifiers. So once we have this discretized form, the next thing is we want to define our conditional probabilities. And so what we need is the probability of A given B. And so the syntax we'll use is the P function, and then we'll have A given B defined by the vertical bar or pipe. So A pipe B means probability of A given B when it's within passes a parameter to the P probability function. So as an example, we might be interested in the probability of braking being selected given a particular distance and speed. Now, since we have this discretized form, the distance and speed provided can be discretized, and we'll actually have examples of it. But in the floating point form, we did not have necessarily the possibility of finding a match. In fact, it'd be very unlikely to ever find a exact match in the table. And even if you did find a match, you probably wouldn't have any statistically meaningful information about it. You would need lots. You need lots of examples of your data points in order to be able to come up with a probability. So by discretizing, we're creating, we're increasing the likelihood of particular examples fitting into these bins, and therefore it makes it easier to come up with our probabilities. So next up, we're going to apply the Bayes rule. And so this allows us to rewrite our probability of A given B as the probability of B given A times the probability of A over the probability of B. And we can restate this in a even simpler form, which is going to help make things easier once we start to analyze the human provided data in the table. So we're going to get rid of the denominator and we'll actually kind of hide it away. We're going to create a variable A and assign it to 1 over the probability of B. So now our with the Bayes rule applied, we just have alpha times probability of B given A times probability of A. So now we can consider some different scenarios where we might be interested in the data in our racing example. So you might have the desire to determine the probability of braking given the distance and speed. So we can apply the Bayes rule, and so the probability of braking given distance and speed can be rewritten as the probability of the distance and speed given braking times the probability of braking. And if we further apply the naive assumption of conditional independence, that means we can break apart the distance and speed into two separate probabilities. And so the probability of distance and speed given braking becomes the probability of distance given braking times the probability of speed given braking. So if you use the Bayes rule and the naive conditional independence rule, you end up with alpha times the probability of distance given braking times the probability of speed given braking times the probability of braking. Now, this is really just moving things around, just leveraging some of the principles of probabilities. And the reason why we want to go to all this trouble is because we want to make it easy to work with the example data we have from our human reference player. So if, let's say we have a particular example, so we've got our table of data, it's been discretized, and then we've got, like, during the game, we have some example state of the game, and the agent needs to make a decision about whether or not to brake. So we want to know, given the distance and speed of the current situation, should the agent brake? That's the question. So the first thing we need to do is discretize this world state that is relevant to this situation, which is the distance and speed. We want to discretize those, but before we can then analyze the data in the table. So in this case, our distance is 792, so that's going to be far, and speed of 12, that's going to be slow. So now what we can do is, using the discretized terms, we can apply the Bayes rule and the naive conditional independence, and that gives us alpha times the probability of being far, given that braking was observed, the probability of going slow, given that braking was observed, and the probability of braking. So now we can look at our table, and since we have everything rewritten in this way, we can easily look up this information. So we can find the examples that where distance is far and braking is a Y for yes. And so we can just count these examples up pretty easily. And so in this case, we have 2 examples, and we can also see for slow the probability of breaking, and slow we see that there are 2 examples, and for both of these they're out of 5 examples of breaking. So for far, that is 2 examples of far given breaking, so 2 out of 5, and also out of 5 for slow. Then we additionally need the probability of breaking, and so we have 7 total examples of breaking or not breaking, but 5 of those are breaking, so 5 out of 7. So this allows us to just multiply out these 3 different terms. So 2 over 5 times 2 over 5 times 5 over 7. That gives 20 over 175, which we can simplify to 4 over 35. And oh yeah, we also had the alpha. So we can also look at sorry, I had to do a little jump cut edit of the slide. So we could also look at the probability of breaking being off, or no instead of yes, but with the same conditions for far and slow. And so this is important in order to actually determine what an action is. So we want to know whether or not to break. So you might look at the breaking examples yes for far and slow, and the breaking examples no for far and slow. And so you want to pick the bigger probability of the 2. And so if you go through the same process of calculating, you'll end up with 1 over 2 for far, 1 over 2 for slow. Again, those are for both with breaking as no, and then the probability of breaking being no is going to be 2 over 7. So what you end up with is 2 over 28, or 1 over 14. So we still got these alphas. So we've got the alpha times 4 over 35 and the alpha times 1 over 14. It turns out that alpha we don't even have to worry about because we're making a comparison of these 2 values. And since we know alpha has to be positive, then it could just as well be a 1. And we would still have the same relative comparison here in terms of which probability is greater. So we might pick to break based on the data and making this comparison. So this fundamental approach can be used to drive selections of different actions, so that you could implement an agent that just analyzes current conditions and selects different actions in this sort of flat rule approach. So you look at what the current conditions are, you discretize the same way that you discretize your human provided data, and then just each time the agent gets an opportunity to make a decision, you just pick the greater probability. But we could also use this to inform decision making with other strategies we've already seen before. So if you, say, had a human make determinations when to switch between different states in a finite state machine, you think of it as like selecting different high-level strategies as conditions change. that might be how the agent determines what are the best transitions to make when. We might also use this with fuzzy logic rules. So we're already needing to create these different discretized state representations for different input values, so that there's already a bit of similarity with fuzzy logic from that perspective. So what we could do is just consider like all combinations of fuzzy inputs and outputs, and so we would have a very large set of candidate rules. We wouldn't want all of those candidate rules, because some of them would be at odds. So for instance, like braking based on the distance and speed, we wouldn't want to have simultaneously brake if the distance is far and the speed is low, or like braking and not braking. So we want to pick one or the other. So but we could have all of these be candidates, and then we could look at the human data, and so that would decide, well, which rules would be present in our set of rules. So we would just need to work out in advance, well, what are the what's the structure of our rules going to be? So for instance, if we're going to have compound Boolean like ands, then we would want to just go ahead and set up that structure and know what inputs are being used for our particular output rules, and then we would need to figure out how to deal with the fact that we might have with fuzzy logic, we'll tend to have degree of membership functions that overlap. So in this case, we need to pick one way or another. So having overlapping degree of membership isn't going to work here. We need to just pick one or the other for each of these human examples, whether we're going to classify, say, a distance as being near or far, or a speed as being low or high. So in this case, we could just, as we're applying the degree of membership function for discretization purposes, when we do have overlap, we just pick the larger one for using the naive Bayes. So if you have, say, a speed that's kind of falling in the middle of low and high speed, you might be, even though they're overlapping, you're probably going to have a degree of membership that's higher for, say, slow than the fast value. And so you would just say, okay, well, this particular human example in our table, we're going to say that is slow because of the higher degree of membership. And so you could use that for determining what are the actual rules are going to be present in your set of fuzzy rules. After that, the fuzzy logic runs as before. So there might be benefit of using, say, this type of a strategy as opposed to just using the simplest form of the naive Bayes classifier, because with a naive Bayes classifier, you're just going to be jumping from one decision to the next based on the current conditions. So you're going to have those kind of hard transitions. So whatever was the most likely choice by a human given the current circumstances, you might have like these hard thresholds that you're transitioning between. So there could be some benefit in smoothing things. So fuzzy logic would be one way to do that. You could also just do a more straightforward sort of smoothing um, of the selected actions just straight from the um, naive Bayes classifier, but that is something you might have to deal with regardless. It is some form of smoothing. You can also, this isn't specifically the naive Bayes classification, but it is leveraging some of the things we've talked about with the Bayes probabilities, is a Bayesian network. And so this can be useful in situations where you have these cause and effect dependencies between game phenomenon. This could especially be the case in, say, situations where you have incomplete information. So the agent might observe something, say, that a human player that's up battling against the agent is doing. So, like, the army that the human is controlling will occasionally interact with the agent, and so the agent will be able to observe it, but can only observe where they have units or structures like buildings. So anywhere out of range of sight of the units that the agent controls, it is unknown. So this concept's called fog of war. In fact, in many video games that are like real-time strategy or turn-based strategy, they literally have a fog that is covering parts of the map, and that depicts where you cannot see. So the agent doesn't know what the human player is doing except what they can see. So let's say that the agent is attacked by a few archers. So the agent might be able to infer that, well, if their archers are present, then that means that there's an archery range present, and therefore that means that the opponent could also train crossbowmen, and maybe they're especially dangerous against certain units or resources that the agent has, and would need to respond accordingly with like a strategy, some kind of protection, build some special armor or protective structures. Now, in this case, that was a very kind of like trivial example based on the figure shown here on the table. But you might have much more complicated structure between these dependencies, and knowing that certain buildings or units are observed, but having an incomplete picture of all of the assets of the opponent, the agent may be able to infer something by applying these Bayesian probabilities according to these dependencies. So certain observations, you can apply the probability of the A given B, and so the given are the observations. So what's the likelihood of certain structures existing, or that certain types of attacks might occur? And you know, these could be strategies that the agent would be especially vulnerable to, like let's say the player, the opponent, is close to the point where they can build aerial units, maybe like blimps, and then drop fire bombs down. And right now, the agent has no protection against aerial units, but they see some hint that maybe the opponent is close to being able to build that, if not already. And so once they get that little hint, well, that you can analyze it through the Bayesian network, and then up the priority on building certain types of defenses, where otherwise it's not worth wasting the resources to build that unless it seems likely. So you can also apply the Bayesian probabilities for this sort of scenario and build a network and these dependencies and probabilities that the agent can learn. So it's a little bit debatable, I guess, how useful this is, because in many cases the AI always has access to the full game state. So why would the AI not just be able to directly access memory and see whether or not the player has something or not? So this gets a little into the issue of fairness and whether it's worth the effort to implement something complicated like this just to try to make it as like authentic decision making as possible versus maybe just doing some cheating but dialing it back a little so it's not too difficult or too obvious. But hopefully you see some of the benefit of some of the simple, straightforward kind of conditional statistics, learning these probabilities, and then being able to apply them to decision making in your agents. Hello. In this lecture, we are going to look at exploration versus exploitation in the context of learning. All right, and so we're going to look at the one-armed bandit problem. If you've taken a machine learning class before, you're probably already familiar with this, but if not, the basic idea is that we're considering a scenario where an agent is playing a game. So we'll start off just by considering the simple problem of observing the payout of a game like a slot machine, or also called a one-armed bandit. So if we're playing a game, well, there's no choice to make other than to continue playing, but we might want to know what the payout is. And so we could observe each time we play, each example where we pull the lever or put our money in, pull the lever, and then see what the payout is. And so we could track this as a probability of winning. And so we'll keep it simple, and there's not going to be like varying amounts of winning or losing. There is just you either win or you don't. And so if you win, that is a positive example, and if you lose, that is a negative example. So you can just tally up the number of wins over the total number of times you've played. So you might have, say, one win for one attempt, and that would give you a probability of 1. Or you might have one win out of 2 attempts. So that would mean like 1 win and 1 loss. So you'd have 0.5. And if you keep track of these multiple times pulling the lever, then you can track, and as you get more and more samples, if you have some fixed payout rate for the game, then you're going to converge on an accurate measure of the payout for the machine. So when you first start off measuring, you're going to be susceptible to chance, just the random nature of the game, as to what your estimate is, what your belief is in the payout. So it'll move around a lot at the beginning, but then it'll converge over time to something that accurately reflects the random distribution that the machine is based on. But so in the case of the one-armed bandit, there's no decision to be made. It is all just, you have to play if you want to win. But what if we have multiple machines? So we may have a whole number of different one-armed bandits that we can pick from. And these one-armed bandits might have different payouts. So if there are different payouts, that means that, well, there's going to be this dilemma. We are going to want to play all of the machines to try to figure out, well, which one is best. But during that process of figuring out which one is best, that would also mean that we're not optimizing our winnings. So we might be spending money unnecessarily just so that we can try to get a better estimate of the payout for a particular machine until we finally are satisfied. And so this dilemma is exploration versus exploitation. So our goal is we want to start making money as quickly as possible, but long term, we want to make sure we're making the most money possible. So if we consider a strategy of exploration, we might have a situation where we have 3 machines. We don't know what their payout is, but we can figure it out if we just keep randomly selecting between the machines. So if we have 3 machines, we can just use some random process like a pseudo-random number generator and pick which machine we are going to try next. So regardless of what information we've collected, so if we're tracking a table like described before, where we know a tally of how many times we play each machine based on the history of wins and losses, then we would expect that we will converge on an accurate estimate, what we believe to be the payout for each machine. But there's never a point where, if we just stick with this strategy, there's never a point where we can now take advantage of this information that we've learned. On the other hand, we could utilize an exploitation strategy. So this is where we'd use a greedy strategy, where we're always going to pick the machine we think will give us the best reward. And this is not really well defined what it means to use a greedy strategy separate and independent from exploration. The simplest thing you could probably come up with is just don't bother with tracking any stats on the machines. Just pick your favorite machine and you stick with it. And so whatever the payout is for that machine, that's what you're stuck with for forever, as long as you're running through this decision-making strategy. Now, we might alternatively keep track of stats and then maybe actually have the potential to change machines. So any possibility of changing machines might introduce some element of exploration. And it does allow us to update our belief based on the tally of the machine. So we may choose, as a first possibility, we just assume the beliefs for all the machines are 0. And so I guess you could also say they're uninitialized, so either 0 or uninitialized. And you could pick the machine with the highest belief. And if there is no machine with the highest belief, like they're all uninitialized, maybe you pick randomly. And then the first machine that you test that has a success, well, suddenly that machine has the highest success. And you will never, in terms of decision making, that value will always be higher than all the others. So you'll never abandon it, even if your first early success is followed by losses and the information you collect maybe converges on a low payout level. So another thing that you could do is, well, you could say, well, rather than assuming that we're going to start with an assumption that the machines have a zero belief, we could instead assume they have 100% belief. So that'd be like a value of 1 for every machine. Now that value by itself doesn't really isn't very helpful, at least in terms of our tallying, because we really need to have, we also initialize not just the win rate at 1, but we also need to have some value in for our tally. So we might assume that we're initializing every machine with a belief of 1 and pretend like we've had some number in of trials where they've achieved that level 1. Now, if you do that, what will happen is for all the machines that their payout is less than 1, that number will shrink over time as you play. And so say you try the first machine, the first loss is going to knock, as you update the tally, you're going to be knocked down from 100% down to something less than 100%, depending on what N is. And then you would pick a new machine. So the greedy strategy of always picking the best machine, we would engage that logic and be able to switch between machines. Now, if that N value, though, is very small, we might suddenly have our value of 1 drop down substantially. So if you initialize with N equals 1, so the first time you attempt to play one of the machines, say it's a loss, you would go from 1 out of 1 to 1 out of 2. So you'd immediately drop by 50%. And then another loss would drop you down to a third. And so some bad luck at the beginning might knock the value well below what the machine's actual long-term payout is. And so bad luck early on could result in the wrong machine being identified in this greedy strategy. So even doing that is not perfect. We could make N very large, but then that means that it takes a very long time to converge where we know accurately what is the right machine. So there's would be a long period of figuring it out, and there's still always that chance that the N was not big enough. There was just such a long unlucky streak that this again, priming with a belief of 1 or 100% guess that payoff with, and then a very large N estimated as, or we're pretending how many attempts had already been made, even though that's not accurate. Another approach you might take is to anytime a machine loses, regardless of what its running tally is, we might just say switch anytime there is a loss to the next best machine. So if you're playing a particular machine because you thought it was the best, but it has a loss, you then switch to the next best. So that helps to get the agent or the process switching machine some to do a little bit of exploration. But the problem is you might still have a scenario where a bad luck streak would push one machine to a low estimate. And then you get to the point where maybe you're just bouncing back and forth between two machines. So you pick what you think is currently the best machine, and you play it until there's a loss, and then you switch to the next best machine, and you play it till there's a loss, and then likely the next best machine when you, that you switch will be the one you started with. So you just oscillate back and forth between those two. And if any good machines were unlucky to get bad short-term stats, then they will never be revisited again. So that's not really a reliable strategy either. So one other possibility that we could consider is that we could just visit all in machines, um, and sorry, we could visit all the machines and visit each in times. So there's some number of times that we will determine that we want to sample, and that will allow us to control how much effort we put into getting some sort of statistical measure of the performance of the machine, and get a good estimate of the probability for the payout. Once we have collected all that information, then we can switch to the greedy strategy and simply use the best one. So that could actually work pretty well. The trick will be making sure that we pick an N that is big enough to achieve statistical significance. So that's going to be a critical aspect to the algorithm. So that is a good segue into another strategy, which is to sort of split up our time between exploration and exploitation. So what I just described is a way to do that, where it's called epsilon first, but more generally, epsilon greedy is really the strategy that's going to be most effective. And so for epsilon greedy, we're really just saying there's a ratio defined for our decision making, and that this ratio is saying how much time are we going to spend on exploration. So we're going to spend most of our time selecting the best machine, so this greedy selection of whichever machine is best. But some fraction of the time we're going to not use our current best estimate. Instead, we're going to try some random machine, and so that'll give us an updated tally of the machine performance. So we're always increasing the quality of the stats, but still taking advantage of whatever the current stats are based on the machine performance. So this allows the algorithm to escape from early greedy mistakes. So even if a good machine accidentally, or not accidentally, but just by luck, had a very bad run, but in the long term it has a higher payout than what that would indicate, then you can recover from that. So if you're greedily selecting the wrong machine, since you're still occasionally spending some time trying the other machines, you'll be able to recover from that. So one way we can analyze the performance of any sort of strategy for trying to take advantage of the multi-armed bandit scenario, and so trying to figure out what's the right way to handle exploration versus exploitation. We could imagine that there is a perfect agent who will always take the best action. So if it's possible, it's like an oracle. If it's possible to get the best choice for any given time step of pulling the levers, whichever machine wins, we'll use that as the baseline of comparison against other strategies. So we can compare the agent's payout, or that agent's payout, the perfect agent, with our agent's payout, and the whatever the strategy is for selecting. And so that difference is that defines the regret. So we can sum up regret across all of the different timestamps, all of the different opportunities to pull the lever, and then that'll give us a total regret up to that point. And so we could compare different strategies by how well they do relative to the perfect agent. So we might get a graph that looks something like this for different strategies. So we've got our time steps on the x-axis, and then total regret on the y-axis. So we would expect that regret would increase over time because we're not going to be able to make a perfect agent. We have random processes, so we don't know what the true best choice is for something that is a random process. But we can compare it, at least we can compare different strategies to one another in terms of the graph. So with the greedy strategy, you'd imagine that you would likely get very quickly to the point where you're just picking one single machine. Now, there might be a little bit of variation early on if we had any of those variations, variants of greedy. So, depending on how we initialize the values and whether or not we're just blindly picking one machine and not tracking stats. So you might have some small bit of a curve at the beginning, but you would eventually likely would settle on one machine indefinitely from some point onwards. So you'd have a straight line. That straight line would not reflect the best possible outcome, because there's that other better machine. So you would have the regret linearly increasing. Now with epsilon greedy, you would also have this linear increase, and that's because you have this exploration cost. So even if you find what truly is the best machine, one-armed bandit to pull, you're still going to be accumulating this exploration tax, basically. And so that after some number of timestamps, you'll have this linear curve, but it will tend to be less than the greedy strategy, because the greedy strategy, at least on average, there's a good chance you would arrive on the wrong machine. But we could modify the epsilon greedy so that we have decaying epsilon greedy, and by that I mean the ratio changes over time. So the degree to which exploration occurs. So I showed an example before where 10% of the time exploration was applied, and then greedy the other 90%. But with decaying epsilon, we might start off with, say, 10, but then we would slowly decrease it. And so if you do that, the idea is that you're going to collect enough information, hopefully, to have an accurate estimate of the payouts of the different machines early in the time steps that are taken. And then we'll assume that we have converged or come close to converging as we reduce the epsilon. And so the benefit of doing this is that once we're satisfied that we have a good estimate of each machine's payout, we then transition to taking advantage of that information. And so this is generally a desirable strategy when you have a learning problem where you're trying to balance exploration versus exploitation. The downside is that you need to have enough domain knowledge to come up with the schedule beforehand. So you need to know how much sampling is necessary before the measurement is reliable, that you can trust it. And so this is something that you would need to tune and maybe be informed by the problem domain in order to come up with this. There's not like a one size fits all decay rate that we could pick from. But the multi-armed bandit problem, it just demonstrates this really simple example of reinforcement learning, and it's important to think about this like this thought experiment and understand how it can relate to other types of learning problems as well. So that's why we went through the example. Hello. In this lecture, we are going to look at Q-learning, which is a type of reinforcement learning that is applicable to video game agent design. So first of all, let's think about learning for agents in a video game. So we might desire to have our agents get better over time through a learning process, and in particular, get better at selecting actions. But this can be difficult to do because you need to give feedback to the agent or the learning process as to what good actions are. But this could depend on, say, unique human player actions that are taken, like an opponent. You can't necessarily anticipate what every player is going to do. Some players might have some very unique strategies, and even if you could perhaps anticipate them, it might be good to be able to have some sort of learning take place to specialize for whatever human opponent is being faced. Another sort of practical issue is variations in the simulation environment. So like different maps that might be loaded. Some of these may be out of the control of the designer, or perhaps the game leverages procedurally generated content. And so this could also cause issues in being able to easily evaluate the quality of actions taken by the agent. Another big problem is determining the quality of an action can't always be done immediately. So if an agent, say, takes a particular action, well, at that moment, they may not have achieved any particular success, like killing another agent or the player, or having acquired a bag of money, or whatever sort of rewards are inherent in the rules of the game may be periodic, and many actions would be taken by the agent in between these rewards. So you can have delayed or time-based effects. So maybe setting a trap for an opponent. So the agent might set a trap. Upon setting that trap, that's the action taken. After that, they're not doing anything related to the trap anymore. But it might have a payoff. So you would ideally want to, any algorithm you come up with, you would want to be able to reward that actions after the fact, once it's finally successful. You can have other sorts of time-based effects, like maybe poisoning an opponent. So like, say the agent fires a poison dart and it does a very small amount of initial damage to the opponent, like just knocks off one hit point for the initial hit. But over time, it might reduce the health of the target much more than that. So you have this time-based effect. It pays off over time. You could also have actions that are part of a sequence, one of many actions. So collecting reagents to create a healing potion. If, say, the first ingredient collected is like mushrooms, Well, there's no obvious way to reward that because there's no success achieved by the agent from just having collected mushrooms. It's not until all the ingredients are obtained and the potion created that we could then finally consider the mushroom collection as having contributed to the reward. So there's lots of these circumstances that are that you would expect to have in a game that have this sort of delayed effect in terms of reward. So any sort of learning that we do, we want to be able to deal with that scenario. So before we get to Q learning, let's first consider Markovian state. So we've previously looked at the multi-armed bandit problem. And so that is a Markov decision process that is a single state or stateless. This is based on the Markov property that given the present, the future does not depend on the past. So it's memoryless, this the approach of the Markov decision process. So everything that the decision making is based on is represented in the state. So we can maybe define a problem as moving between states. So there's nothing that like that the agent needs to remember or store internally. Simply it can act on the state information. And if everything that is needed to make these decisions is within this state representation to make an optimal decision, then it is Markovian. So Markov decision process, we have a finite set of states. And then for each state, we have a finite set of actions that can be taken. For each action that we might take in a given state, there is a probability that it will take us from state S to some new state, S1. And we might associate with, if assuming that transition actually occurs, we can associate some reward with that. Furthermore, we have this discount factor, and this is used to tie together the reward that might be gained in the future states. So you have reward associated from going from, say, one state to the next, but then also going to that new state, there is reward obtained with this by way of this discount factor, which is blending current reward, like from the current transition, but also future reward. And so if we can break up representation of the world into these states and actions, then we can imagine we have this ability to optimize and figure out from any given state what is the best action to select probabilistically, like what's most likely to give us the most reward, considering not just the going from the current state to the next, but also the chain of states that we could go through. So finding this optimal action is, we're going to have a process we're going to call the policy. And so this is just taking the, for whatever the current state is, what is the optimal action to take? So we're rewarding transitioning from any state. And so this reward function is based on what states we're transitioning between. And so the idea here is that we can give these rewards or feedback to the Markov decision process on what are the best actions to select from. So we want to head towards certain states that are related to success for the agent. And these could also be rewards could be negative. So like we could punish rather than reward as well. So we could use both approaches of reward and punishment. So we can we have this probability of going from these states, and so this is sometimes called a forward model, but we're saying that not all actions taken guarantee that we move from one state to the next. So you might choose to perform an action, but the agent in selecting it is not always going to be successful for some reason within the details of actually running the game simulation. That might be, say, Mario moving across the screen, maybe could bump into something, maybe an enemy hurts Mario and causes a failure of being able to move. Now these probabilities are generally defined, like in the context of a game, they're generally defined in more abstract sort of way. So you're not saying that from a specific coordinate in the map that there is a percentage chance of being able to, like, say, go to the right one unit. Instead, this is more generalized. So it's would be based on, like, from any square, what's the possibility of moving, say, to the left or the right. And so you can have these percentages or likelihoods of being able to change between these states. So provided that you have this probability, so you have the states and the actions and the probabilities of getting from one state to the next, and then you define the rewards, you can analyze all of your states, and you can figure out the policy for which is the best to go through. And once you have this information, you can calculate very quickly what is the best action, because it's all just table lookups. But the issue that you run into with this process is, well, what if you don't have that transition function, the probability of getting from, like, state S to state S prime? So if you don't have those, or don't have a good way to define that, then that makes it difficult to use the Markov decision process. So, but what if we had a means of learning those transitions? And so that's where Q-learning comes in, and it I think it is likely in many games that you would not be able to, other than some of the more simple games, you would not be able to easily just engineer what those probabilities should be. But if you could learn the transitions, then that would make this much easier to apply to video games. So similarly, with Q-learning, we represent the world as a state machine. So the state encodes all the relevant data about the agent environment, just like before. So if it's important for making the decision, it needs to be encoded in the state. And if the information is not in the state, then, well, is not available to be learned. So therefore, the agent will just not be able to ever act upon it. So one of the nice things about Q-learning is it doesn't need to understand what makes up the state. You just need a way of mapping the game state to the Q-learning state. And so this is why Q-learning is referred to as being model-free. So you have to have some process that's going to perform this mapping for you. So you can think of it as like a discretization process. You may have games that already have discrete state, like a grid lattice type positioning. But if you have, say, floating point representations of certain values, then you would need to discretize those. But the actual Q-learning state can just be, you can just refer to it as an integer. Once you've performed the mapping, all you really need beyond that is just a unique name for it, and that can just be an integer. And there's no need to be able to translate back the other way. So the Q-learning is just operating on these identities. You can think of them as simply just being nodes in a graph type of structure. Now, with each of the states, you have associated actions. So in some games, all actions are always going to be available. But in many games, you're going to have context-based actions. So you can only open a door if you're near a door to open. Might be the sort of situation that an agent could run into where there's this context. And so you can probably imagine there's lots of games that do have this sort of contextual sort of actions. So you also have to, in order to utilize Q-learning, you have to be able to identify and associate available actions with each of the states, likely discretized states that you create. You also need to be able to give feedback by way of a reinforcement function. So this is after an action is taken, you're going to have this metric that determines whether to reward or punish the agent. Now, in many cases, you might simply just return 0 because nothing interesting happened at that moment. But you could have positive feedback, or negative feedback. So the overall range of values returned will tend to be from -1 to 1. Many cases just returning 0, but on the occasions that something important happens in the game that you can associate with success of the agent, you'll return somewhere between 0 and 1. Or if there's something bad that happens, somewhere between -1 and 0. Now there's some flexibility here with the Q-learning approach. So there's no requirement that feedback or the reinforcement function return needs to be the same every time the same action is taken in the same state. But Q-learning can't learn to act on any missing information that may have caused the discrepancy. But at least it'll tolerate it. So if there is something is like, say, not encoded in the state, the discretization maybe threw away something that causes the disparity. That's okay. The algorithm will tolerate it. So that's something nice about it. Now you can also have situations where states can change independent of actions taken. So in other words, always taking the same action won't always lead to going into the same state. And so here's a nice, just simple example that Millington gives about this sort of situation. So imagine you have a world state that's been encoded, and so we'll just have some minimal details for this example, but we'll say, so this is like a combat game. There's an enemy near, so we've encoded that so that you can either have an enemy near or enemy gone. In this case, the current state is the enemy is near, and the agent can be hidden. So let's say the agent is currently hidden, and they take the action of hide to remain hiding. So with the opportunity to make a decision or pick an action, they pick to hide, to continue hiding. And perhaps the next update of the simulation, the enemy is still near, maybe still looking for the agent. And of course, the agent is still hidden. And so it would make sense for the agent to choose hide again. So clearly you wouldn't want this to just continue on forever where there's no progress made. But let's say the enemy decides to leave. So this is a change in state that was beyond the influence of the agent's decision making, the selection of action. The enemy leaves based on its own action, but that changes the state. So once you think of an example like this, it becomes sort of obvious that, okay, yes, state can change for reasons outside of the agent's action the agent takes. So if the enemy leaves, the new state is going to be enemy gone and hidden. Of course, in this change of state, now the agent is likely to pick to do something else. The enemy is no longer around, so it could pick a new action, and it's in a new state, picks a new action, and can do whatever might lead it towards reward. So just in summary, Q-learning is flexible with this type of uncertainty, either of these cases. So each time there's an opportunity for a decision to be made, we can represent that with this experience tuple. So this is, it's just like a record of what occurred. There is the current state, there is the action taken from the current state, a reinforcement value that's generated. This is the feedback scoring how they did. Again, it could be 0 or something else depending on circumstance. And then there's the resulting state. So this information defines the action at any given point that's taken by an agent. So next up, we get to the actual learning that takes place with Q-learning. So the agent is going to be learning by managing a set of quality information scores called Q values. And these are associated with each possible state and action. So when you're in a given state, you'll have actions, and then for each of the actions within that state, they each have their own Q value. And the Q values represent belief in the action, so associated with the state. And so this is some, this will ultimately provide us with the information that we need for selecting the best action to take. But this leads to an equation that we have, so we can figure out, well, what's the Q score for a given state and action selected? And so that is shown here, and it's got a few different parameters that allow us to tune the learning effect that takes place. So we have like a table of all of these scores. So whenever an action is selected, well, we can take the previous Q value, and we will have a contribution of the previous score plus this updated score. And so we use an alpha value to control this ratio. So there's 1 minus alpha defines how much of the original score is going to be preserved in the updated value, and then alpha times this new score, which includes the reinforcement value, and then also this other bit with gamma times max. And so that is the gamma is the discount rate. And so the discount rate, that is controlling how much of future states contribute to the score of the current state. And the discount rate as a parameter allows us to control how much benefit we get from those future states. So in particular, the max of that Q S prime A prime, that is based on whatever is the best action from the next state. So once that transition from state occurs, well, it's going to have its own set of actions. One of those actions is going to be the best one based on the ongoing learning that's taken place of having run through Q-learning multiple iterations. And so we want to contribute whatever the best score is to the Q value that led to it. And so if we go back again, so we can see how we're again using perhaps the majority of the score is what was there before, but then we're incrementally revising the score based on the reinforcement plus this discount rate times whatever state it's leading to, and the value or belief that comes from it. And so we can control how much of the new state contributes by adjusting the discount parameter. So as you recall, compared to the Markov decision process with Q-learning, we don't need to know the transitions. We're actually actively learning those through running through the Q-learning algorithm. So in terms of exploration, we have a policy that determines what actions to take in any given state, but the policy isn't trying to strictly just pick the best, like with the Markov decision process. We actually need to go out and collect data. So we are, from the perspective of Q-learning, the game itself is like a black box. It needs to be sampled from by attempting actions and getting results back. So we need to learn about the quality of the actions in each state, but we also need to take the best actions to further expand the overall best course of action. So if we just explore completely randomly, that will mean that it'll take us a really long time to build up the data that we need in the Q values in order to reflect these chains of actions that we're trying to identify. So we probably want to use epsilon greedy, perhaps decaying epsilon greedy, to control when and how we select actions. So we might tend to want to pick whatever has the best score currently, but we also want to occasionally randomly pick an action that's not appropriate. And so you can see more discussion of epsilon greedy strategy in the multi-armed bandit lecture. And this exploration, we might want to pick different strategies for exploration depending on whether we're doing offline learning, meaning like where we might be running the simulation of the game, but that is during the development process. So there's not like a human player that we're trying to entertain. So that would be offline, and so we could perhaps afford to be more performing more exploration. Whereas if it's online, you will want to really limit how often you're randomly selecting an action, because would anytime you do that, there's a chance you're going to get some really oddball behavior from the agent that's going to confuse the player or frustrate them because it might appear as like a bug in the game. Why did the agent do such a silly thing? So you have to really consider what the scenario is in terms of how you tune the exploration. So the algorithm involves is really pretty simple, at least from a high level. Is you initialize Q values to some value. And then you're going to choose an action from whatever the current state is. And again, recall that we have some external process that's always figuring out what state we are in. And this is, at least if we're running it with a simulation, we will determine our current state by the discretization process. But then we're going to have to choose an action that's associated or available in the state. And so we would use the epsilon greedy strategy here. So we might pick greedily, or perhaps it's an exploratory selection of an action. So you perform the action, and then you receive the reward that may or may not be an immediate payoff. You might get a value of 0. But then you're going to update Q, and that will perhaps be chained together the score with whatever the next state is based on that discount factor. And so that's going to then, so you're now in a new state and can pick a new action again. And you just can repeat this process over and over. And you're probably, at least in a simple case, you just have like a 2D table. So you just, by index of the state, you can look up the row and then the columns to define the different actions that are available to you. And so when you perform the calculation, the updated Q value calculation, that's what you're updating, is whatever the value is stored in the table. So pretty straightforward. In terms of performance, we'll have big O of I in time, where I is the number of iterations of learning. And then in terms of memory, because of that table we just saw, that is the number of states times the number of actions. And so of course, these tables can get rather large, and it really depend a lot on how effectively we can create this discretized representation of the world, keeping in mind that every bit of information needed to make an optimal decision needs to be encoded in the state. Otherwise, you're going to get less than optimal behavior. Now, it might be a worthwhile trade-off to have agents that don't perform completely optimally, but that are still suitable for a video game. So there's perhaps some room to work in terms of the design of the discretization process. Millington has some recommendations for the parameters with the Q-learning. So if you have the book, you might want to actually read the whole section, but just some highlights where he discusses this. Learning rate of 0.3 is his recommendation if you're using a fixed epsilon greedy. Sorry, not epsilon greedy, but a fixed learning rate. But if you are going to, you might vary this according to a schedule based on the number of iterations. So you might start off in earlier iterations where the learning rate is really high of like 0.7, but then map that down as a function of I to 0.1. But if you're not going to do that, just use the fixed value of 0.3. Discount rate of 0.75 was his recommendation. And so he has a bit of discussion about what is favorable depending on how long of sequences that you might desire. I believe the 0.75 can get you sequences of around, and by sequences I mean a chain of states, actions selected to move from state to state. So that would be around 10 actions total. But so he has this recommendation of 0.75. Higher values favor longer sequences of actions, but it's going to take longer to learn. But if you have lower values, you're going to stabilize more quickly, but only have like some capped shorter number of sequences. Randomness for exploration. This is really important to set according to whether you're online or offline learning. So again, online meaning live during the gameplay with your target audience playing the game. And offline is just if you can you train separately, and then the resulting table is what you ship with the game. So online, a value of 0.1 is about the maximum that you can go with. And that's, again, to try to minimize the agent doing really dumb things that seem odd or are detrimental to the gameplay experience. And then offline, it's only a little bit higher for the exploration. So it's 0.2 is Millington's recommendation. And that's, again, what I discussed previously is that even if it's offline, you still need to visit the favorable states because you want to be able to learn the chains of states or the chains of actions that lead from state to state for the purpose of the back propagation of the Q scores. Millington also has a bit of discussion about rewards. And so there's obvious sorts of scenarios, like if the game can be won. So you would give like a reward of a 1.0. Need to be, however, cautious about incremental rewards. So the game designer or the AI designer might perceive some actions or moving from one state to the next as being progress towards the goal. It might seem obvious to the designer to reward that. However, when you create these sort of incremental rewards, you can create scenarios where there's like a local maxima, and the agent will end up in these circumstances with Q-learning. They'll just go in a loop obtaining these small rewards. So they might pick a sequence of actions that lead in states such that they come back again to that same reward that had been configured. And they'll never even discover that there's, say, a path to the winning the game with the 1.0. They might just keep picking up a 0.1 score over and over. So Millington recommends you start only rewarding success or the preferably like the one way to be successful, and then only add in other solutions or small rewards if the learning is taking too long, or you're just getting poor results. Maybe the agent's just never even able to discover the appropriate course of actions that ever like lead to winning the game, for instance. All right, and so to summarize, Q learning. So it's a very general decision making technique. It's model free. You don't have to do much in the way of engineering software that's specific to your game, other than just the mapping of the game, the discretization of game state into the Q learning state, identifying the actions that are available at each of these states, and also defining the reward. And of course, the tuning of the different parameters is also important. But otherwise, you have this very general algorithm and approach that can be used. Downsides, however, though, you have this massive potential for state space size, and that can also lead to a long time to learn. When you do have this large state space, it can take a good bit of training, and it's really most appropriate for offline learning. There's like I believe Millington mentions like an order of magnitude is a reduction in the number of states is really practical if you're going to have online live learning within the game itself. So Q learning is I think an interesting approach, and that maybe has some potential. There's if you're interested in more discussion, Millington has a few other examples that he goes into, but I think one thing he suggests is not using it for complete agent control, but using for some subset of the decision making of an agent. But yeah, definitely something, a strategy that's worth considering, especially if you value learning in your agent